Aku ini udah masuk YouTube ya, Sis?
Ecosystem in Indonesia with two main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums.
Good morning. Welcome to the second day of 2025 International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications, or ICRAMET 2025. For the second day of ICRAMET 2025, we will have two keynote talks, we will have 5 parallel presentations, and we also have one patron speaker, and ICRAMET 2025 will be closed by the closing ceremony, including awards announcements. And I will do the outline for the second day of ICRAMET 2025. For the first agenda, we will soon hear the third keynote talk by Dr. Hee-won Kim from Cortec Limited, South Korea. And next, we will hear the fourth keynote talk by Professor Dr. Nasrullah Armi from National Research and Innovation Agency, or BRIN Indonesia. And following a short morning break, the agenda will continue with the parallel sessions of 6, 7, and 8 at 9:50 a.m. UTC +7. And after the lunch break at 1 p.m., there will be 2 breakout rooms for parallel session 9 and 10. And after we completed all the parallel sessions, we will hear the third pattern talk by Dr. Andri Mahendra from Patenics Lab. And the ICRAMET 2025 will be closed by the closing ceremony, including the awards announcements before we are closing the ICRAMET 2025. And I also would like to extend our gratitude again to our esteemed patrons, Andritsu, Unitronic Jaya, Rode and Swartz, PT Mars System Integrasi, PT Nix Lab Global Industri, PT WAP Andalan Indonesia, PT Serviam Abadi Murni, PT Radar Telekomunikasi Indonesia, PT Mitra Sistematika Global, PT Sapta Cakra Manunggal, PT Merck Chemicals and Life Sciences, PT Dreamtech Lab Science Indonesia, and PT Bank Rakyat Indonesia. Thank you for your valued support in bringing this conference, and we will come again to opportunity to work with you in the future. And now, without further ado, we are starting our first keynote talk. I believe that we already have Dr. Hee-won Kim with us, right? Dr. Hee-won Kim, are you there?
Yes, I'm here.
Oh yeah, okay.
Thank you very
Welcome.
much.
Yeah, thank you. Okay, so I will invite Dr. Hee-won Kim and also our moderator for today, Dr. Malin Ramadan Baidillah. Please come to the stage. And before starting the keynote talk, I would like to introduce to you to Dr. Malin Ramadan Baidillah. He currently works in Research Center for Electronics in National Research and Innovation Agency, or BRIN Indonesia. And he received his PhD degree in mechanical engineering from the Division of Artificial System of Science, Chiba University in Japan. And he also been a research fellow with the Multiphase Flow and Visualization Laboratory in Graduate School of Science Engineering, Chiba University since 2018 under GSPS Postdoctoral Fellowship and Chiba University Fellowship. And his research interests include sensing, imaging, and tomography system for biomedical and industry applications. Please welcome Hee-Won Kim, PhD from Cortec Limited, and Dr. Malin Ramadan Baidillah.
May I now share my file?
Check, okay. Check, okay. Okay, thank you so much, Miss Adita. Very good morning, audience, ladies and gentlemen, in offline or online. So finally, we have arrived at the second day of the conference, and today's session is the keynote speech from Professor Kim. Professor Kim, can you hear my voice? Is it clear?
Yes, it is very clear.
Okay, so before we hear the presentation from Professor Kim, I would like to read some short CV. Please confirm whether it is correct or not. So we apologize if there is some things wrong. So the keynote speech today, the name is Hee-Won Kim, PhD. He is currently the CTO of Cortec and former faculty member at the University of Southern California. Oh, sorry, there is some different. This is ISOL or Cortec. So please confirm, Professor. Sorry. And he has advanced human in vivo MR imaging and spectroscopy toward novel methods such as myocardial perfusion assessment, and currently leads national R&D programs in ultra-high field MRI and MR guided HIFU systems. So the title today from his keynote speech from the program's book, it is From Airwaves to Body Waves, RF as the translator of MR imaging. I think it's fine. Okay. Yeah, so Professor Kim, welcome to the keynote speech, and time is yours now. You can start your presentation.
Thank you very much. Would you allow me to share my file?
Yes, please.
Okay, thank you, Dr. Baidillah, and I welcome you all. I'm very grateful for invitation of the organizing committee of ICRAMET and Dr. Ruli and other members from BRIN Indonesia, especially the audiences participating in this very early morning on the second day of the conference. Okay, now, the title, From Airwaves to Body Waves, describes the RF as the bridge between communication and MRI. Both fields fundamentally rely on the same core RF principles: signal generation, transmission and reception, modulation, noise control, and antenna design. Well, even though I'm no antenna engineer,
Recording in progress.
I'd like to share the essence of such a viewpoint from the MR scientist perspectives. The same waves that carry your voice can also form an image of your living body. Johannes Kepler. I love to begin this talk by mentioning this 16th century astronomer and a natural philosopher and a writer even on music. In describing the orbit of planets, he was the one who transformed his mentor, Tycho Brahe's precise observation data into mathematical laws. This marked the beginning of model-based reasoning. That is the belief that mathematical models can reveal the hidden order of the natural world. He says, if a phenomenon can be mathematically reproduced, then its mathematical structure reflects the truth of nature. MRI's imaging theory stands on the very same philosophical foundation. We mathematically reconstruct the invisible internal structure of the human body from measured signal, like phase, K-space data, or projections. In other words, we perform a mapping from the unobserved reality, anatomical structure inside of our body, to a measured mathematical representation. This process runs perfectly parallel to Kepler's endeavor, deriving the invisible orbit of the planets from their observation, Tycho Brahe's positional data. You now know the Ford problem as a computing the expected measurement from the given model. That is the physical law of the system and parameters. On the other hand, the inverse problem as estimating the unknown model parameters or structures that produces given measured data. Then, what was Kepler's inverse problem? Kepler replaced ideal geometry like a perfect circle, like this, with physical truth, the ellipses. His idea is model nature as it is, not as it should be. Kepler solved an inverse problem, deducing invisible orbit laws from visible positional data of his mentor, Tycho Brahe. Modeling the planetary orbit is the Kepler's inverse problem. This is a deep analogy, the Fourier-Kepler connection. By revealing that planetary orbits are not perfect circle, but ellipses, Kepler recognizes the limit of purely periodic linear approximations to real-world data. Imaging theory, especially MRI, it decomposes and reconstructs nonlinear, irregular signal patterns through Fourier-based representation, effectively approximating aperiodic structures as superposition of periodic functions. That is the Fourier transform. In both realms, the move from ideal circles to elliptical or Fourier representation marks a deeper understanding that nature's complexity can still be captured through mathematically structured yet flexible models. Again, the forward problems, we compute the expected measurements from the model, and in the inverse problems, we estimate the unknown model. Then, what is MRI's inverse problem? The process an MRI coil receives a signal is based on Faraday's law of electromagnetic induction. When the magnetization vector in your body rotates over time, the resulting time-varying magnetic field induces EMF force in the receive coil. In the Bloch equation, it is the difference in equation, as you know, describing time-dependent behavior of nuclear magnetic resonance, or NMR. It shows how to magnetization interacts with magnetic field, showing it precesses like this and relaxes. And precesses, relaxes over time. Now, the ingenious idea behind the MRI lies in encoding spatial information into frequency and phase. By applying gradient magnetic field, this is the gradient magnetic field in your body, the phase of each becomes dependent on the spatial position R. As a result, the signal measured by the coil can be expressed as the following Fourier integral equation. So this is in the body structures, and S is the signal. So that is the K-space signal equation. The K-space is the spatial frequency domain. We stores the raw Fourier encoded signal information, and that is later transformed to an image like this by doing this inverse Fourier transform. In other words, the signal S measured by MRI coil is a Fourier transform sample of spatial spin description like this. Now, when NMR data acquisition is complete, what we obtain is S. By applying inverse Fourier transform, the actual image M can be reconstructed. Through this process, the data are transformed from K-space to image space. That is from the frequency domain to the spatial domain. That is MRI's inverse problem. The analogy between Kepler and the MRI can be understood in this way. object of observation, Kepler's were motion of planets. Ours are internal structure of human body. Observed data, his is celestial position. Ours are signals in the spatial frequency domain. Mathematical transform, he found elliptical orbit, and we are doing Fourier transform. And the outcome is orbit model, and ours are reconstructed image. What is the essential goal? His is expressing natural laws. Ours are reconstructing human body structure for many targets. Now, the most crucial elements lies in observed data. In the analogy, transmit-receive resonator known as MR coil, corresponding Kepler's celestial position data, the interface through which invisible structure becomes observable. So our second topic is about this, signals in the spatial frequency domain throughout the MRI RF coils. Now we are ready for a second part of the talk. We need to understand three forms of resonator: conventional antennas, MRI RF coils, and the human body. In conventional communication system, the antenna acts on transducer that converts electrical currents, of course, into EM waves throughout the free space. And MRI, the RF serves a parallel but distinctive role. It translates the EM resonance and nuclear spin precession. The reason for using translator metaphor is that the ultimate role of MRI is to faithfully generate and convey the language of spin precessions to both transmission and the reception with precision. In short, antenna inside of MRI radiates into the air, but the RF coils resonate within the tissue. This is a human body, and unlike free space, the human body is an inhomogeneous, lossy, and dynamic medium, a complex mixture of tissues with different permittivity and conductivity. Each region of our body, brain, fat, muscle, alters all local field distribution and coil impedance. As a result, tuning and matching are not static, but interactive process between the coil and the body. Most recently, we view it as a form of electromagnetic communication. The coil continuously adapts to the body response to maintain optimal information exchange between electric circuit and nuclear spins. Electric circuits of RF coils and nuclear spins in our body. So antenna for MRI is RF coils, and historical evolution is it starts from the first loop coil, and it is flat, and it goes to solenoid, and it evolves to the volume coil like a saddle, and finally birdcage coil. And then phase array idea introduced. That makes simultaneous signal acquisition possible. Now, nowadays, multi-channel design also enables parallel imaging. It is very important to accelerate the speed of the MRI, and that improves signal-to-noise ratio and the speed. And improved signal technique is always a great issue for this area. And adaptivity is, I just mentioned the previous slides. As standard antenna design does, impedance matching ensures, as you know better, ensures maximum power transfer, minimum reflection, and stable operation of the RF system. And in the MRI context, perhaps the perfect matching means uniform excitation. That means accurate B1 field in your body, high signal-to-noise reception, reduced coupling, and reduced the damage for specific absorption rate, SAR. And in one word, safe and efficient power use. Another engineering principles regarding coupling between coil elements, because nowadays we have used many coil elements. The crosstalk is important, and crosstalk is unwanted electric coupling between adjacent coils. It leads to detuning, field distortion, noise correlation, and signal-to-noise ratio degradation. So there are many suggestions to solve those problems, like geometric overlap, preamplifier decoupling, and high impedance or metamaterial-based design. It is another a little redundant principles: electromagnetic field generation, coupling mechanisms, and impedance optimization. So, antenna engineering impact advancing MRI RF coil technology. To looking at the past of the RF coil for MRI and its evolutions, the first, it was simple single coil elements. And the shape has been changed to excite the volume, like this saddle shape. So like this saddle or solenoid coil was applied, but it produces non-uniform B1 field, leading image intensity variation over the spatial variation. Then core innovation comes up in the birdcage form. A cylindrical resonator structures like this, and it consists of two end rings, and multiple rungs, and capacitors distributed along rings and rungs to control resonance. It is truly capable of generating highly uniform, circularly polarized B1 field within its volume. So it has been achieving homogeneous excitation, the transmit part, and reception, the receiving part, across large body region, especially head and torso in MRI. Now, the array coil like this represents next great leap after birdcage. If the birdcage coil solved the problem of homogeneity, the array coil solves the problem of speed and sensitivity of localization. The array coil introduced the concept of multiple independent receive channels, like this. It increases signal-to-noise ratio through proximity to anatomy, and it enables parallel imaging for accelerated data acquisition and allowing flexible coil geometry to fit different body parts. Decoupling network to minimize mutual couplings is required, and parallel imaging techniques like a sense, that is sensitivity encoding, and SMESH or GRAPPA is K-space synthesis, is now available. It also paved the way for phased array transmission for B1 shimming and parallel excitation. I will mention later. Yeah. Wireless, flexible, and wearable coil arrays too, and AI-based adaptive coil tuning and reconstructions. Now, high field challenges. Why do we develop ultra high field? That means more than 7 Tesla MRI for medical use. Yeah, it is about 300 megahertz range. It is not simply use stronger magnet, but rather to overcome the fundamental limits of MRI in signal-to-noise ratio, spatial resolution, and functional sensitivity. S70, the effective wavelength is shortened to approximate 10 centimeters. So spatial interference happens, B1 field inhomogeneity happens, signal loss and distortion in deep region. So there are many techniques has been developed. For example, the parallel transmission and transmit array like this. So it is now 64 channel receive array coil or 96 channel array coil. So it can be partially or overly solved even in the high field challenges. Not only challenges, there is an excitement for ultra high field because other nuclei rather than proton can be examined more easily at ultra high field of MRI. Because the most of our image came from the proton, but we also wanted to know the other nuclei like sodium, like phosphorus 31, carbon, and fluorine. But their problem is their signal is too weak. But as you increase your the magnetic field, it increases linearly. So this one is the imaging, the example of the sodium imaging. And sodium imaging is used for neurology and kidney disease and the tumors and so forth. P31, it also phosphorus 31 metabolites is involved in the human the energy metabolism. So this is ATP peak, and it is ATP peak is our energy currency, and phosphocreatine is energy reservoir, and we can see the change of those peaks. What are you doing in your body? Like ischemic heart problems, why he is doing that kind of symptoms, and why do the muscle are becoming so fatigued, and someone recovers fast and someone does not, something like that. This is the multi-nuclear resonator looking at your brain, not only the proton, but also the other nuclei. So what is the trend and futuristic MR coils or coil systems? One option is high temperature superconducting materials. So not only using the copper wire, but you can using high temperature superconducting magnet materials. Of course, you can use low temperature superconducting materials. It is much harder, cheaper. Looking at the Q values, when you reaches superconductivity, your quality factor is over 2000. It is enormously high. So that means it is very low noise signal you can detect. So that means the realm of low loss resonator, making it particularly advantageous in MRI application, such as NMR spectroscopy, cryo probes, and ultra low noise receive coils. This is another one. It is metamaterials. It is high impedance surface. High impedance surface acts phase compensator between the coil and the human body, locally flattening the magnetic field distribution. So in multi-channel array environments or others, HIS acts like an RF lens, redistributing magnetic field lines more evenly across the volume. Also, HIS isolate between elements even without decoupling network. It is important. You don't need decoupling network. So HIS suppresses surface current propagation. So it can be very safe. And also high surface impedance by reflecting electric fields while sustaining magnetic field. HIS structures lower the local tissue heating. It is the material for the future. Now, it is the nowadays it is still vague, but this is the direction of the RF coil goes to. So adaptive or smart coil are advanced MRI RF coils. It integrated on-coil electronics, real-time feedback. So it makes this digitization not in the console, but in the local network or local coil. And AI-based control is possible. Adjust coil performance during scanning. That is very fascinating, one. And also, they move beyond static, pre-tuned design. It is self-optimizing RF interface that adapt dynamically to the patient and scanning conditions. So when even human factors changes, when you breathe, when you move, it changes accordingly. That is very smart and that is very adaptive. What is shimming? Shimming means to make excitation field more uniform inside of the body. To do that, you adjust amplitude and phase of the B1 field. So in the high field MRI, they are all work is focused on the shimming. Especially 70 and above, field non-homogeneity and SAR management becomes dominant. So this is the most active modern MRI coil system design frontiers. How do you do that? You can collect the input data and make a deep neural network and training and SAR constraint and real-time prediction makes possible and closed loop adaptation. So it is done by AI and it can also be shimming. Because when we do the elaborate test, the shimming time is vast. So once it is materialized, it would be really great. In short, AI-driven shimming teaches the MRI system to think like an RF engineer, not human, but the systems. So from manual tuning to intelligent self-tuning, from fixed shim to adaptive electromagnetic cognition.
Professor, 5 minutes lapse. Thank you.
Okay. Wireless system in the Y gig bands, you can do the complex, you can remove the complex coils and cables. So I'd like to introduce the RF coil design, Quartech and Korea University like this. This is for 70. It is not monopole, but dipole. And you are looking at the wide range of the coverage. It is very significant for 7 Tesla MRI. So looking at not only the brain, but also the entire cervical region. You can compare it with conventional NOVA coil, only this. This one is not easy for 7 Tesla MRI because 7 Tesla, the wavelength is very short. Another one is multinuclear RF coils, and it makes the sodium imaging possible, and it is well done at 7 Tesla. And it uses deep learning, the Maxwell tomography. So it is not the rigorous Maxwell equation, but the fast Maxwell. And it is high intensity focused ultrasound. We can guide using MRI. And there are enormous interaction between the Hive system and the MRI. So MRI image is pretty bad. And looking at to solve those problems, there are blocking circuit and make 1,024 channels. That is HIFU, the circuit, and it interferes, and it reduces those interference like this from this. This image is not that appreciated, but in the MR guided Hive system, it is good one still. And this is another, I can make the video possible. Oh, okay, you can see it. You can see the dynamic monitor from the Hive systems. And because MRI can measure the inner temperature, so that is the temperature image. So it is all done in the Cortex systems and using the RF coils designed and manufactured in Korea University. AI assist RF coils, I'd like to skipped because of the time constraint, but in short, surrogate electromagnetic modeling, that is fast Maxwell, and optimization, design, space exploration, and AI-driven RF streaming, and intelligent tuning and matching and decoupling, and specific absorption rate and safety predictors, and co-design of human and RF. These are all mixture that AI can build those platforms. The surrogate EM modeling is important for fasting Maxwell, and the closed loop, and it senses and solves itself. Now, in conclusion, back to Johannes Kepler. The great Kepler, his wonderful fulfillment, now we enable us to see this. And his homeland, this is the Keplerstrasse, the great Kepler. But Kepler's all fulfillment wouldn't be possible if there is no Tycho Brahe, his mentor, and his meticulously precise observation. So Tycho Brahe is the cause of the Kepler's fulfillment. Do you know what it is? This guy died 5 days ago, This is 1962's Nobel Prize ceremony, and Watson and Crick and Wilkins got the, have a Nobel Prize for physiology because of the finding of DNA structures. But their achievement wouldn't be possible without the Rosalind Franklin's diffraction X-ray patterns. I'm sorry, she died 4 years earlier, so she was not joining the Nobel Prize. This is the great MRI. Amazing the blood vessels. This is the hippocampus. You may not feel, but this is amazing hippocampus structures. And statographic to tractography to make our neurons. And this is functional MRI. It is not possible if there is no RF coils. So we need the coils that faithfully translate the signals into our MRI system. So in the closing remarks, I'd like to recycle my abstract, part of my abstract, that MRI ultimately speaks in the language of electromagnetic waves, and it is MRI as a form of communication. And MRI coil does not only broadcast, it converses. It talks. It gives you talk sometimes loudly, sometimes very softly. This is MRI coil and our MRI systems and our body and the world. Thank you very much for your attention.
Okay, thank you so much, Professor Kim. Very nice presentation, starting from the philosophy until the future direction. Please give applause, everyone. Thank you so much. So, before I go to the audience, I also very interesting, Professor. So many questions. Please let me give you some very basic questions. So usually, in the emergency, Professor, so doctor prefer to use CT scan. For example, such a case, let's say to detect the ischemic stroke, it's very important. We need to real-time imaging systems. So that's why doctor usually prefer to use CT scan as the modality for that one. However, the stroke itself is basically a soft tissues case. So in the theory, in the real practice, MRI could be better, so the image of the stroke itself. But MRI is considered very slow. So the problem now, how to make the MRI construction faster, and then, yeah, in the emergency case, 1 minute's order is very crucial because it's lifetime matter. So any idea, suggestion, point of view from you about how to make it more faster and suitable to be applied the emergency case?
Of course, MRI, the real-time imaging is one of the great area of MRI. Usually when you do the T1 weighted imaging, T2 weighted imaging, diffusion weighted imaging, and so forth, you can easily at least 5 to 10 to 15 minutes to scan. But you have to make fast, and it is possible. When I see the MR guide high intensity focused ultrasound machine, you can make we have made 4 frames a second. So you can make the MRI image 4 frames, 4 MRI image in 1 second to use extremely short echo time. You may not familiar with the echo time, but the echo time is very important to make the image possible. So there are the image echo time and so forth. So not only the soft not only the simple soft organ, but the heart, the moving target. You can see even the moving target like the liver or the pumping heart. You can see the motion on the real time. So there is a big part of the MRI. I visited last February the National Brain Hospital in your capital, and I forgot the doctor names. He oversees the nationwide stroke program. So you guys have the over 17,000 islands. So when you run those the stroke program, it is crucial to see the CT, but CT is pretty bad, not as good as MRI for soft motion. When you see the stroke, it is very important to see this is the real stroke or not, and that the stroke is the hemorrhage or it is blockage. It is very important, and we need MRI. Then that technique is required, and it can be easily implemented.
Thank you. So regarding to this, some researcher, I saw some from South Africa, for I'm not mistaken, they try to make the portable MRI. So it's very short, very small. Yeah. So how do you think about the portable MRI feasibility for this case? Is it, yeah, okay, we can continue to make this one, or how do you think?
Yeah, the frontiers of the portable MRI, like hyperfine, they have the pro and cons. And pro is obviously it is mobile. Mobile MRI is fantastic, but their magnetic field is 680 Gauss. So it is very low, about less than 20 times small. And obviously the resolution, speed, and the image quality is pretty bad. And there you can improve by far using the AI help. So in the very time critical conditions, like in the emergency room, you can see exactly the as far as I know, the hyperfine machine mostly used in the clinical side, in the emergency room, to looking at the stroke patient. So even though it is a very limited application, it still is it still is available. It still is beneficial. But I wanted to mention that hyperfine is used the real magnet. So if you can replace that magnet into the natural magnet into the superconducting magnet and make it lighter, then it is more versatile. The company I belongs to also looking at the mobile MRI. I can't say it is mobile, but it is movable. So you can still move because it is about less than one cubic ton. Then there are some ways to between the quality and mobility.
I see. Okay, it's great. Do we have question from the audience here? You can raise your hand. Do Volin? Okay.
Good morning, Dr. Kim. I'm
Mhm.
Valin Octaviani from Research Center for Telecommunication. In our research, we usually use an antenna as a sensor for the body detection. For example, for detecting the presence of tumor or cancer. And for antenna, we usually use as parameter such as reflection coefficient reflection for data processing. So if we use RF coil, what type of data that we need to be processed? Is it still using as parameter, or there are other type of data use? That's my question. Thank you.
Yeah, including as parameters, the mostly when you build in the design process, the most important one is the Q values, and because the loading of the body is different, so the Q always changing, and so how to make the real load is close to the real patient in the clinical side. So what, as you antenna engineer and antenna scientist, what is loading changes? That is the key to make the design of the antenna. So as I mentioned in the AI assisted tuning and matching dynamically in the bore, then it would be helping. So once that makes S factor or Q factors, whatever, in the lab, in the bench, and then it can be, if you adapt those AI-driven assisted tuning and matching the locally, then it would be the great.
Yeah, I think that's the answer. Are you satisfied? Satisfied? Okay. Do we have another question from the audience in the Zoom meeting? Maybe. No. Okay, Professor. One last question from me. AI application that you mentioned previously in the slides, mostly it is for to adjust automatically in the measurement parameter, so that the measurement becomes more accurate. I'm wondering whether we can replace the inverse modeling with the AI, machine learning, to make image reconstruction more faster, maybe? Do you think it's possible or feasibility about this one?
Your question is not only the RF side, but the image
Yes,
reconstruction.
that's right. Yeah.
Okay. It is already been done. Their signal reception and image reconstruction, that part. So signal part, AI also involves, and image reconstruction part, AI also involved. These are two different types. So this one, you can easily accelerate even the AI assisted. For example, the undersampling and so forth. And this one is two. So the very fast signal reconstruction. And they in the many hospitals, there are error signs or error images and blitz in the image is found. That means AI is not perfect still. So that is very important because it could be the positive or negative. So the false positive and false negative. So, but the number of those false images are declines like this.
I see. Fantastic. Thank you so much, Professor Kim. That's a very nice presentation, keynote speech today. A lot of things we can understand from your presentation. Mostly we are researcher from RF, microwave, not only high frequency, but also low frequency as well for diagnostic, imaging as well. So this is a good opportunity to us to make further research collaboration. And just please let me know that if you already have a plan to come Indonesia again, we hope that in the future we can meet each other, whether in Indonesia or other country, in Korea maybe. So, so finally, thanks again, Professor Kim, for your keynote speech. Audience, please give applause to Professor Kim. And this is the token of appreciation from us. Thanks again for coming and give your presentation in this keynote speech. See you again.
Thank you, Dr. Padilla. And it's my honor to participate and give you a keynote speech. Thank you. Thank you very much.
Thank you.
Thank you, Dr. Malin. And also thank you, Dr. Hyewon Kim, for delivering us the third keynote speech. For Dr. Hyewon Kim, we would like to have photo session after this. So we'd really glad if you still open your camera soon. And I also would like to welcome Marsikal Muda TNI Insinyur Wajariman, MSc from Defense University of Indonesia. Thank you for joining the ICRAMET 2025. And now I would like to invite all of you to do the photo session to commemorate the second day of ICRAMET 2025. So for the on-site participants, I would like to invite you coming to the stage, and also for the online participants from Zoom platforms, I would like to invite you to open up your camera in the Zoom and turn on your video, because we will have the screen capturing also for the online participants. Thank you. Okay, please coming forward. Yeah. Oh iya. Gak apa-apa ya. For the online participants, please open up your camera. Thank you. Enggak, emang enggak. So are we ready? Okay. Okay, Mbak Christine, are we ready? Okay, so everyone, so strike your pose. What is the first pose, Mbak Christine? Okay, the first one is a formal pose. Also, people in the online Zoom, be ready. So we'll have in 3, not yet. Nggak apa-apa. Nggak apa-apa, biar gampang. Okay, in 3, 2, 1. Again. Oh yeah, still formal pose. Okay, also online participants. In 3, 2, 1. Yeah, okay, the last pose is your expressive pose. Okay, everyone in 3, 2, 1. Okay. Okay, for the final one, we have in 3, 2, 1. Okay, the last one. 3, in 3, 2, 1. Okay. Okay, thank you everyone for participating in these photo sessions, and also thank you to the online participants for having contributed to our screen capturing session. Okay, please have a seat and we will continue to the next agenda. Ya, ready. Okay. Okay, now moving on. We are gonna hear the fourth keynote talk, and we also already have here with us Professor Dr. Nasrullah Army from the Research Center for Telecommunication, National Research and Innovation Agency Indonesia, and he will deliver the talk, and the session will be moderated by Dr. Iman Firmansyah. And I will explain to you his short profile. Dr. Iman Firmansyah works as a researcher in the Research Center for Telecommunications, National Research and Innovation Agency Indonesia, BRIN. He received his PhD in computer science, and also he continued to the postdoctoral position in University of Tsukuba, Japan. Then he joined Indonesian Institute of Sciences since 2005, or currently known as BRIN. His research interest is signal and image processing using field programmable gate array (FPGA), also embedded systems and IoT. Please welcome Professor Dr. Nasrullah Army and also Dr. Iman Firmansyah.
Oke, Assalamualaikum warahmatullahi wabarakatuh. Distinguished guests, participants, and ladies and gentlemen, welcome and thank you for joining us today. This morning, on the second day of the 2025 International Conference on Radar Antenna, Microwave Electronics and Telecommunication. So, today with me, Iman. It is my great honor to be a moderator for this wonderful session. So, in this morning, we are privileged to hear from experts discussing about the next generation industrial IoT, unleashing Industry 4.0 with dynamic and intelligent spectrum use. So, but before we begin, please allow me to introduce our keynote speaker. Okay, this is our keynote speaker, Professor Dr. Nasrul Almi. Currently, he is a director of the Research Center for Telecommunication, National Research and Innovation Agency BRIN. He completed his PhD degree from University Technology Petronas, Malaysia, focusing on cognitive radio. Okay, everyone, please join me in welcoming Professor Dr. Nasrul Almi. Professor, please, you may now proceed with your keynote speaker. Please begin.
Ya, Assalamualaikum warahmatullahi wabarakatuh. Good morning. First, I would like to thank to Dr. Iman for introductions and the committee who invite me. Actually, I'm happy to share the ideas regarding this title, Next Generation Industrial Internet of Things, Unleashing Industry 4.0 with dynamic and intelligent spectrum use. We can see that this current condition that all connected devices with the growth IoT devices with a spectrum crunch. This is we use traditional spectrum allocation with the congestion, and we are moving to dynamic and internet intelligent spectrum use with IoT connected devices. My name is Nasrul Almi from Research Center for Telecommunication, National Research and Innovation Agency. Thanks. Yeah, this is the outline of my presentation, introduction. Introduction will introduce our research institute, Telecommunication Research Center, and one of funding programs hosted by ORE and Research Center for Telecommunication as well. And then we're coming to industrial IoT revolution and its connectivity demand, the critical challenge, spectrum crunch, and introducing the paradigm shift from static to dynamic and intelligent spectrum use DISU, and core enabling technologies, architecture framework of DISU enable industrial Internet of Things system, tangible benefit for industrial operation, and use case across key industry pair to implementation challenge, and the route ahead, and finally conclusion and vision. Yeah. Sorry. Yeah. This is a research center for telecommunication. Yeah, we have 4 research group. Yeah, research group communication and signal processing, led by Prof. Agus. And the focus of research on millimeter wave baseband signal processing, audio video signal processing as well, millimeter wave, terahertz communication, and LiDAR, radar signal processing, and so on. And the second research group is antenna propagation research group led by Prof. Dr. Yuyu Wahyu. The research group focus on the antenna, wireless antenna, microwave device, and so on. And the third research group is advanced network protocol. The focus on the improving network protocol, wireless sensor network, and so on for the application like disaster and all the wireless network. The fourth research group, RF, radio frequency, microwave, antenna, microwave, acoustic, acoustic and photonic research group, led by Dr. Asif Aminullah Fatan, focus on RF, microwave devices and acoustic communication and photonic optic, And this is kalau pointernya pointer. This is a vision to become a dependable, professional, innovative, and trustworthy research center with national and global impact, as well as a reference for developing government policies in the field of telecommunication. To cut this vision, we divided 4 missions. We improve the quality of human resources and research funding with national and global impact. We send the researcher to get the PhD degree and send the researchers also join the training and postdoc and visiting researcher outside. And then the second mission, we expand national and international networking and collaboration. We collaborate with the private sector in Indonesia and also in the outside, overseas like university and private company also. And then the third, increase participation in national and international scientific activities, join conference like ICRAMET like this, and improving research infrastructure. This is our lab. We have 5 lab, communication and signal processing lab, function simulation room for telecommunication, radar imaging, etc. And we have tool and equipment like oscilloscope, spectrum analyzer, and so on. And mostly the user is researcher from communication and signal processing, private sector, university, student and lecturer, researcher from university as well. And this is RF, microwave, acoustic, and photonic lab. We have 2 room labs. The upper side is optic and photonic labs, and the bottom is RF. We have equipped with some tools and equipment that can be used not only RF map researcher, but university from student and lecturer, and also private sector. This is antenna and propagation lab. This is we have tool the equipment like VNA, signal generator, signal analyzer, and so on. And same as the another lab that the user is researcher from antenna, RF map, university, student lecturer, and private sector. And we invite also company from the private company to use this with the regulation implement. And this is most active lab, yeah, led by Dr. Arif. Audio visual transmission lab. We have tools like PC with inside simulation software to the LiDAR monitor and so on. And the users is the researchers, university student, and private sector as well. And this is the last lab located in the Serpong, yeah, in Jakarta, Serpong, Advanced Network Protocol Lab. We have many servers here, yeah. The function is development of telecommunication and network protocol. The user is NP researcher, university, like student and academic, and private sector. You know that we have research funding hosted by ORE. We have research program funding hosted by Research Organization of Electronic and Informatic BRIN, funding program telecommunication of IoT. This is the name of funding programs. We have selected proposal 79 and funded proposal 34, and we selected flagship research of 5. Selected by the committee, we have 5 flagship of priority research that funded by ORE. This is the first research IoT-based early warning system for multi-patient heart rate and respiration monitoring system, FMCW radar. We detect the breath using radar and then send the data to IoT, yeah, send the data to IoT with a multi-patient, and we compare the data detected with the oximeter. And this is the second flagship result, IoT and nanobubble technology-based water quality monitoring system. This research activity monitor the quality of the water, yeah, treatment efficiency and diseases control to improve the efficiency monitoring of the farming system. Yeah, we can see validation can be done with industrial scale test compared performance with conventional system. We equip with machine learning system this activity to optimize feeding and predict fish growth. And this is the third activity, development of on IoT, monitoring air quality assessment. And this is development of Internet of Things system for combined liquid pass. This is for autonomous multi-agent fast charging electric vehicle. And this is the fifth IoT-based design development of RFID. We can see that this to check nutrition in soil to improve the farming system. Yeah, we equip with drone. This under research. We hope will be finished this year or next year. We can see that many IoT devices equipped with the sensor. So we are coming in the industrial 4.0 era, or we are in industrial 4.0 era. So drive the rise of a smart connected enterprise, the Internet of Things with a heavy industry, because you know all devices connected to data transmission. So we think that this will be heavy industry. AI and big data drive autonomous operation, a word of smart factory, predictive maintenance, and agile supply chain. So we have to think how to solve when the device connected or the transmit the data will be heavy. So we have to think what's about the spectrum exists. This is the explosive growth of industrial Internet of Things. Billion of devices trillion of data points by 2030. We check that IoT connection are projected. Yeah, and then sensor are every machine valve and conveyor belt connected to sensor and transmit the data. And then autonomous guided vehicle and drone become standard. Vehicle to vehicle communication, sensor equipped in vehicle, so will be transmit the data. So what about the connection? High resolution video for quality inspection and security, it need wider bandwidth. So we have to think about how to transmit the data when all devices connected sensor and transmit the data. The lifeblood of IoT is data, yeah, from raw data to operational intelligence, vibration, temperature, acoustic, process control, real-time actuator command, and asset tracking, location, and status of good equipment also transmit data. And we have to think about the safety and security, video analytic, and gas leak detection. The connectivity is very imperative. Mission critical wireless is non-negotiable. We need 90.9% uptime required. And what low latency, less than 1 millisecond for closed loop control. And then more than 100, yeah, 1,000 devices per kilometer per square. And then guarantee performance, not best effort. So we have to guarantee the connection is successful. The looming crisis, wireless spectrum crunch. Wireless spectrum is set public resources like land, traditional band like we have 2.4 gigahertz band. This is unlicensed spectrum. 5 gigahertz are congested. Yeah, we have Wi-Fi. All the spectrum is used by the devices in this spectrum 2.4, 5 gigahertz. Licensed spectrum like cellular is very expensive and scarce, yeah, congested by the devices connected to transmit the data. The result, interference, yeah, downtime, and data loss. Consequence of the spectrum crunch when connectivity fails. When connectivity fail in industry, connected device transmits data, costly downtime. A hard production line can be stopped, yeah, per hours. Compromise safety fail, communication with autonomous system, and poor quality, inconsistent data lead to defective products, and inhibited innovation, inability to scale IoT deployment. Yeah, this is the old way, static spectrum allocation. The rule is very rigid, inefficient, and obsolete. Set and forget channel assignment. And then fix a frequency band for specific technology like Wi-Fi and Bluetooth Zigbee. Inefficient use. Yeah, a license band can be idle 80% of the time in location. No adaptability to changing RF environment. We regulate with the static spectrum like satellite communication, cellular network, Wi-Fi, Bluetooth, and so on. And we had to think we need a smarter approach. Yeah, the question is how can we create a wireless environment that is dynamic, not static, efficient and intelligent as the industrial processes that support. Yeah, we have to shift, yeah, from old paradigm to the new paradigm. Like from static to dynamic, we can say that dynamic and intelligent spectrum use, DISU. This is a fundamental shift from static allocation to dynamic sharing. Yeah, from static sharing to dynamic sharing. Network and devices that autonomously send the spectrum and learn the environment and adapt the power and so on, using the right frequency at the right time for the right purpose. This is the principle of dynamic spectrum access. We the three pillars of DISU. Yeah, first sensing. Yeah, listen before talk. Yeah, sense continuously monitor the radio environment. And after that, we analyze identity fileable spectrum holes and predict the traffics. Is it less traffic or full of traffics? And the third is adapt. Adapt means seamlessly reconfigure transmission parameter. We can see that this is a static. Yeah, in the left side, you can see the spectrum is charged, congested with the connection existed. And the right panels, we can see the same signal dynamically organized by AI brain into non-overlapping lanes, maximizing the flow. Yeah, we can see the difference here. Yeah, from the chaos to ordered, managed by design. But we need the enabler technology. What we can use when we move to the dynamic spectrum access. The enabler technology one is AI. Yeah, AI is very popular. It's implemented also in dynamic spectrum access. Yeah, artificial intelligence and machine learning, the brain of the operation. This AI forecasts period of high spectrum demand. Yeah, and then we reinforcement learning AI agent learn optimal spectrum sharing policies to trial and error. So learn the model and the spectrum, and then AI also detect the anomaly. Yeah, means identify the mitigate rogue devices of a jammer. And then the enabler technology too is cognitive radio and CDR, software-defined radio. This is the agile hardware. Yeah, you know that cognitive radio is a smart radio that can change its transmission parameter based the environment, and software-defined radio is hardware where component filter modulator are implemented in software base, yeah, enabling extreme flexibility. And then together they form the physical platform for DISU, dynamic intelligent spectrum use. And the third enabler technology is a spectrum sensing and database, the environment awareness system. I mean the multiple devices, in collaborative multiple devices share the sensing data to create real-time RF maps. Yeah. So RF spectrum is mapping by the collaborators sensing, geolocation database, a central registry that tell devices with primary, like military TV channel, are unused in the specific geographic location. Like we use TV white space that unused by the user. And enable technology for advanced wireless standard, the rule book for configuration. Like we band bring the power of 5G to share spectrum with built-in listen before talk. Yeah, you talk, but you have to listen first. Yeah, Wi-Fi 6, yeah, 6A and 7 feature like OFDMA and multi-user MIMO allow for more efficient spectrum sharing. Yeah, among many devices and wireless regional area network IEEE 802.22, a standard specifically for using cognitive radio over TV white space. This is the architecture for DISU, yeah, framework coexistence. We have a device layer. This is a IoT sensor, and then AGVs, yeah, autonomous guided vehicles, camera with cognitive SDR capabilities, and then edge layer, local DISU controller from real-time spectrum allocation, and network layer, 5G core, private network connecting to cloud, and cloud orchestration layer. This is a center of AI, machine learning for long-term strategy and analytic. How it works, the DISO cycle, yeah. Dynamic mechanism, a continuous loop of automation. First, you have to monitor. Yeah, you have to monitor the spectrum exists. Like RF environment and application, it are continuously monitored. Check the availability spectrum that are used by the devices. And then you have to plan. Yeah, you have to plan. AI engine compute the optimal spectrum allocation strategy. And then when the spectrum is available, then you have to execute. The device can execute. Yeah, command are sent to devices and network element. And then you have to learn. You have to learn system performance fit back to the AI model for improvement. When you access the spectrum, then you have to learn continuously. If the device license want to reuse, so you have to leave the spectrum. Yeah. And this is the benefit, unprecedented reliability and resilience. Uptime become reality, proactive avoidance of interference and congestion. Yeah, self-healing network that root around problem, guaranteed connectivity for mission critical control loop. And this is the benefit too. Massive scalability, grow your network without growing your problems. When you implement dynamic access, so you can grow your network without growing your problem. And dynamic sharing allow for an order of magnitude increase in connected devices, and no more manual frequency planning for new deployment, and the network intelligently makes room for new devices. Ultra low and deterministic latency. Yeah. So the latency need for industrial Internet of Things is less than 1 millisecond. So you can reach this target with the dynamic by avoiding congested bed. Data take the fastest possible path, and essential for closed loop control, collaborative robotic, and AR, VR for maintenance, and operational efficiency and cost savings. So for industrial, this is efficiency is crucial. So drastically lower cost from troubleshooting, interference, and network downtime, and reduce reliance on expensive license spectrum, and they transmit only when and where the spectrum is clear. Use case, introduction, DISO in action, transforming industry. So manufacturing, logistic, energy, and mining. If the DISO is implemented, this is the use case. First, you have to implement in the industry, like manufacturing, logistic, energy, mining, and hopefully this can run and working smoothly. This is a smart factory, yeah, seamless coordination in dense environment, that all industry autonomously and connected with the devices, sensor equipped in the tool and equipment. So when the DISO is implemented in this factory, then we hope we can avoid the stop of the industry due to spectrum crimes. Smart warehouse real-time asset visibility. This is a use case too. The challenge is thousands of item tracked via RFID and sensor, metal shaving, cause signal reflection, and dead zone. And the solution is a DISU, a mesh network of cognitive reader, yeah, cognitive radio reader. They collaboratively send and adapt to find the best path for communication, ensuring that 100% inventory visibility. Outcome, eliminate lost asset, optimize picking route, fully automated inventory count. And this is a use case 3, oil, gas, and gas predictive maintenance, mission critical monitoring in remote location. So you can imagine when the oil and gas company equipped with the sensor and working automatically. So with the DISU, connection is working smoothly. And smart grid dynamic energy management also it is possible to use DISU that connection will be smooth with equipped with the sensor transmitted data as well. And this is automated mining, safety and efficiency. We can check that this mining company equipped with a sensor, also autonomous haul truck and drilling rig in a fast, DISU solution, a mine wide private like using LTE and 4G network with DISU. The system use AI also to predict the movement of equipment and pre-allocated spectrum resources. So how to implement PAS 1 access and strategies? First, we have to audit the RF environment. We have to map current wireless usage and interference sources. We have to make a priority for the application, identity, mission critical versus best effort traffics, and then technology evaluation, access vendor for DISE capable hardware, SDR, 5G, NR, new radio, unlicensed. And then we have to prioritize business case development, quantity to ROI from reduce downtime and increase efficiency. And pass to a pilot and validate. Start with control, high value area, deploy of DISO solution for a specific problem, and collect performance data, uptime, latency, and throughput. And then the refine AI model and operational procedure. So we can expand the DSU network to cover the entire facility, integrate with existing IT, or OT system and network management platform. And then we can develop a center of excellence for ongoing optimization. Key technology partner building the ecosystem. We have focused network infrastructure vendor like a Cisco, Ericsson, Nokia, industrial automation giants like Siemens, specialist SDR cognitive radio provider, because this is the enabler technology that will play the crucial thing in the dynamic spectrum access and cloud and AI platform. The challenge when we implement DISU, system complexity, the intelligence comes with a cost. Because this is a new technology, DISU systems are highly complex, software-defined system, and require new skill in RF engineering, data science, and software development. Then solution, we can cooperate with a partner with expert and invest in a training system. Standardization and interoperability. This is also the challenge when we implement the DISU, dynamic spectrum access, ensuring devices from different vendors can operate in dynamic spectrum environment. Evolving standards are still being finalized. The solution, we can choose a vendor committed to open standard and industrial alliance. And then the challenge, 3, security. You know that the wireless is possible to attack, a new attack surface. You can, intelligent network is a potential target for AI power attacks. So the solution is implement security by design, zero trust architecture and robust encryption for control signal. The challenge, the next challenge is a regulatory landscape. You know, the regulation is very important also to implement the standard of wireless. Regulation for dynamic spectrum access vary by country and are still evolving, like in Indonesia as well. Solution work with regulators and industry group to set a favorable policy, demonstrate safety and non-interference. The future is cognitive and collaborative by DISU, the self-optimizing industry network. Fully integrated digital twin. The network is live, a digital twin of the physical operation. We have a predictive resource allocation. Yeah, we have many spectrum access in the wireless standard, so we have to predict the resource allocation that congested, so we can optimize the spectrum use. And cross-domain coordination, spectrum sharing between different factory of even across supply chains. Call to action for industrial leaders: start your journey now. Don't wait for connectivity to become the bottlenecks. Yeah, because when it's stopped at the industry and the production will be halted. Initiate an RF audit for your key facilities. Include DISO in your long-term digital transformation long map. And invest in research and development, because you know that the investment in research development is costly hike. Yeah, so we have to prepare, develop hardened and industrial grade SDR platforms. So I know that the telecommunication researcher here has capability to use the SDR as well. Champion interoperability and open standard. And conclusion, yeah, the strategic imperative connectivity is the new competitive edge. Yeah, next generation of industrial Internet of Things demands a next generation wireless foundation. Dynamic and intelligent spectrum use is not a feature. It is the core enabler for the resilient, efficient, and autonomous industry of the future, because you know that the devices grow dramatically. So we have to think when the connection, the connectivity, when the connection is stopped, then what happen will be the production in the industry. The time to build that foundation is now. We have to be action. Thank you, and we give back to the moderator.
Okay, thank you very much, Professor Nasrullah Almi, for insightful and inspiring presentation. So we also would like to thank for giving us a deeper understanding of how the latest technologies such as DISU or dynamic intelligent spectrum can be implemented in industrial IoT. Okay, and now finally we move to the Q&A session. So for those of you who have a question, please raise your hand. And then for all the virtual attendees, you can write your question on chat. We will read them for you. Okay, is there any question? Okay, while we are waiting for the question, so I have question, Dr. Nasrullah. So as you mentioned that compared to the traditional wireless network, the DISU offer the advantage. So you mentioned that DISU, how to say, address some issue or limitation compared to traditional. So I would like to know, is there any limitation or drawback of the DISU implementation, for example, in terms of cost and regulation and so on?
Yeah, thank you for the question. As I mentioned in the slide, the final slide, like we have challenge, yeah, when we implement the DISU, dynamic spectrum access intelligence spectrum use, that previously the old regulation is a static. Static is spectrum is, it is has been point out with the regulator. This is for like license. We have two license and unlicensed. So unlicensed 2.4 gigahertz and 5.0 is very congested with the user. So the challenge is first regulation. Regulation is the main challenge. Yeah, we have regulator like Komdigi, how to access the spectrum. Is it possible to implement the spectrum dynamic? Because you know that is very hard to the spectrum. This is the root spectrum for satellite, for cellular and TV also. So how possible to, for example, user can shift and move from one line to another line, like from licensed spectrum, this for frequency 2.4 gigahertz to another spectrum. But if it is supported by the authority, like regulator, I think there is no impossible. So we can implement, like you know that the crisis of due to the, if we cannot find the solution for that, so the spectrum will be congested. Yeah, the spectrum will be how to manage the billion devices connected with the data transmitted. So this is will be very difficult. So we have to find a solution. The main challenge is, I think, regulator. Yeah.
Once again, how about the cost?
Yeah, the cost is very. I don't know the fixed cost. The number is I'm not sure, but very high, I guess. Yeah, very high. The cost is so high because we implement the new technology. We have to attract a new expert system. We have to build the new technology also. It's maybe can cost costly.
Okay, thank
Yeah.
you very much. Okay, ladies and gentlemen, is there any question? Okay.
Yeah.
Okay, thank you. I interested in the explanation about the system, but you mentioning about the situation when the system is in chaos. My question: can you elaborate more about the chaos if the chaos is coming from the outsides of the system or the platform? How do you mitigate the situation in this condition? Because for us as a user, sometimes uh, the enemy from outside will introduce, will coming to the system. So please elaborate more about how you mitigate the chaos from outside if the system working. Thank you.
Yeah, thank you for the question. Yeah, the chaos will be happen when the devices connected grow exponentially. Like the devices connected is transmitted the data from industrial and so on. But today, the device is still under managed. Yeah, so the chaos is not visible today. But when it happened, we have that the solution is a dynamic spectrum sharing, because we have a limited spectrum. We have a limited spectrum. So how to arrange to manage the spectrum congested uh, with the order, yeah, like the spectrum can used by user smoothly, and that's managed by design. Uh, we have a technology like MIMO and FDMR. This is a technology for modulation and multiplexing, but it is not sufficient. Yeah, we have to uh, technology that very extreme, yeah, to change the congested system. I think uh, yeah, I think that's my point. Yeah, my answer today is today connection is not I think this under managed because we have limited devices today current, but we think by 2030 or 2045, the device is connected, industrial equipped with the sensor that transmitted the data, and then vehicle to vehicle communication equip the sensor and transmit the data. And then also this is maybe a room equip the sensor then transmit to the data. You have to think how to manage the congested this transmission. So we have to shift from the static management, like a static spectrum use, to the dynamic spectrum use. I think that's my response to the question.
Okay. Is it okay, Mr.? Okay. So we have another question from virtual attendees from Mr. Ananda Kusuma. The question is, spectrum is a scarce resource and it is always associated with price. Can we incorporate spectrum pricing to AI-based issue?
Yeah. Yeah. We are not using license spectrum. Actually, yeah, we have to pay for some prices with the license spectrum, but we can use unlicensed spectrum that not used in the unlicensed user. So I think it's possible. Yeah, it's possible to use the spectrum with AI based DISU. Yeah, because you know AI technology is the possible enabler technology that can be implemented in DISU uh, uh, with another technology like cognitive radio SDR and so on. Then AI is the platform that very crucial when we implement the DISU, because AI can learn the map of the spectrum. Yeah, so we can use the data bus from the AI sensor, yeah, to access the spectrum that we can put memorize for the spectrum access spectrum access, because AI is the tool that can be equipped with the DISU. So I think we can possible to incorporate spectrum pricing to AI. That's my response.
Okay, thank you very much, Professor Almi, for your answer. I hope the answer from Dr. Almi can address your question, Mr. Ananda. Okay, because of the time limitation, so I guess it is the time to end this session. But once again, thank you very much to Professor Almi for time and your expertise that have shared with us in order to improve our deeper knowledge. And then to all participants, please join me in giving warm of applause to our keynote speaker.
Yeah, okay. We have the token of appreciation for Professor Nasra Almi. Okay, so I would like also to invite Professor Yusuf Nurwijayanto to give out the another token of appreciation to Professor Nasrul Armi. Okay, thank you once again to Professor Dr. Nasrul Armi for having brought our fourth keynote talk for ICRAMET 2025. And also thank you, Dr. Iman Firmansyah, for having moderated this session. And before we have the morning break, I would like to remind you for the parallel session. So we have three different rooms for parallel session 6, 7, and 8 at 9:50 UTC plus 7. For the parallel session 6 will be in the main room, and for the virtual presenters from Zoom platform will be in breakout room 1. And for parallel session 7 will be held in breakout room 2. And for the on-site presenters, it will be inside the Kinanti 2 meeting room at the corridor to the right of the door. And for the parallel session 8 will be conducted in the breakout room number 3. And also, I would like to invite you to visit our exhibition booth to the left of the corridor. So for those of you who are interested in antenna testing, radio frequency or RF testing, and also interested in material characterizations, you can visit the Rohde and Schwarz booth in the left corridor. And they also have the vector network analyzer and XO5 digital oscilloscope. So you can ask and discuss with Mr. Taufan Pega. And for those of you who are interested in the area of photonic chip testing, material characterization, and also battery testing, you can go to the next lab exhibition booth to the left of the corridor also. And they have for people who are requiring low power needs that need source, measure, and control. I would like to invite you all to come to the exhibition booth and also having your refreshment at the corridor. Thank you.
Deck, which consists of hardware and software that we created in-house. We integrate our device with the semiconductor chip industry to help them reduce their cost for testing and get more reliable and also high yield of their product. The current problem in the semiconductor industry testing for the chip is because the current equipment is bulky, expensive, and also not integrated. Our solution provides technology that's 20 times smaller, 3 times cheaper, all integrated with easy-to-use software. Our device analyzing the reliability of the chip. This reduces the amount of defective chips and also puts out high yield in the manufacturing. It is important for the semiconductor chip manufacturers. So we have shipped our product to over 15 countries. Now also being used to different applications such as the AI, quantum, and also in data centers. NASA used for the space, US Army for defense, and NVIDIA for the AI. For those companies, they use our equipment to be integrated with this chip to make it function properly in different applications. One of the best functions of our product is provide the voltage and current. Our equipment helps guide light so it can work properly into different applications. We are inspired to create more innovative devices so we can help people to have a better life around the world. This motivates our team every day.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Organization for Agriculture and Food, Research Organization Economy and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with two main targets. BRIN cultivate human resources with high competence and aptitude in science and the form of BRIN's commitment to researchers, innovators,
The spirit and mindset of our founders live on today and continue to evolve from one generation to the next. Every day, thousands of employees worldwide benefit from the knowledge that is accumulated in our company over decades. At Roda and Schwartz, they learn from each other, showing respect for that which came before them. We're part of this world and pass on our knowledge by providing the best possible solutions and systems. We've never made a secret of our innovation culture. At Roda and Schwartz, excellent development performance and entrepreneurial behavior go hand in hand. We make a difference. Driven by our distinctive passion for technology, we create the innovations that are highly relevant for a safer and connected world. Our customers and partners know they can always rely on us to deliver the highest quality. We are strongly positioned and look forward to a successful future. Our mission is clear: make ideas real. Yesterday, today, and tomorrow.
let me remind you that we have 9 to 11 minutes for presentation time, followed by 5-minute Q&A session. And then for the online presenter, please turn on your camera during your presentation. Now let's moving to the first presenter, Mr. Yaswan Nanjapa from Manipal Institute of Technology, India. The floor is yours.
Okay, good morning all. Thank you for the opportunity and inviting me. Yeah, so can I have my slides, please? Slide changer. Yeah. Yeah. Ah, okay. Okay. So, yeah, my research paper title is Long Range Underwater Energy Harvesting Power Bank System for multi-source applications. So before starting my presentation, I would like to thank the organizers of this conference, ICRAMET 2025, and my university for giving me an opportunity to come here. Yeah, so let us start with the introduction. So underwater wireless sensor networks are essential for monitoring and exploring aquatic environments. So we have two types of wireless networks. One is the terrestrial wireless networks and another one is underwater wireless sensor networks. So my main objective here is to just see how the energy harvesting can be done in underwater environment, because in terrestrial environment there is ample opportunity or lot of chance to replace the battery. But in underwater wireless sensor networks, whenever the sensor node is deployed in water, we might not be able to find the sensor nodes to replace the battery. So that is the main intention behind this research. So
Recording in progress.
My research team is Mr. Mahesh Kumar, who is my PhD student, my colleague, Dr. Bhaskar Avadia, and my external, like the student's external co-guide, Dr. Niranjan Yusi. Yeah, so coming back to the introduction, so traditional battery-powered nodes are difficult to replace, as informed. Energy harvesting from renewable sources such as solar, acoustic is sound, and thermal energy offers a sustainable power alternative. Yeah. So in the system overview, that is proposed system overview, so a centralized power management system is considered, which which is connected to the different cluster heads. So whenever we talk about network, we'll be having lot of cluster heads in a network. So cluster heads is like the sensor node which is having the highest energy. So that might be having a bigger battery to transmit the data as well as to communicate with the neighboring nodes. So in this simulation environment, we have considered 10 cluster heads wherein it has the battery and the neighboring nodes just have a small battery capacity to just be a feeder between the cluster heads. So here, intermediate power banks share energy with distance nodes for efficient operation. So the technology here, which is used, is magnetic induction, which enables simultaneous data and energy transmission. Since, as informed earlier, the batteries drain out after some specified duration and frequent replacement of batteries are not possible, we propose an energy harvesting technique which is obtained from the solar energy. Considering this whole screen as the water environment, the solar panel will be placed about the screen. It will take out the energy. So magnetic induction, I think I can connect it when the toothbrush doesn't have a connection directly, but still it can send the energy, or it can power up the electronic toothbrush with the help of magnetic induction. Yeah. Yeah, uh, this is done. Yes, I was just talking about the water environment. The solar panel, yeah, solar panel is at the surface level. The energy management system manages the total power which is received by the solar power. And we have numerous cluster heads. And next to the cluster heads, we have sensor nodes like these dots. So this indicates the sensor nodes, but this is the cluster head wherein the battery is placed, the main battery is placed, and the power is obtained from the solar system. Sorry, solar panel. Yeah. Next slide. Okay, so the implementation strategy is deploy clustered underwater sensor nodes with integrated power banks. Next is energy harvesting and transfer. Energy harvesting done through the solar panel, and transfer is done with the help of magnetic induction, and monitoring and control to implement comprehensive real-time power monitoring and notification feedback systems, because all when we talk about network, it should always work in a synchronized fashion, sending the data efficiently within the specified network. Yeah, this I'll not go through the maths as such. This is a math for energy harvesting through solar panel. So we find the total energy harvested by the solar panel during the time interval delta t. So this is the power demand of the cluster. So this power demand is the total instantaneous power demand of the cluster within the network. This is the energy level of the power bank, wherein we find the remaining energy level of the power bank at time t, because I'll be showing you the graphs wherein we can see all these operations happening within the network. Yeah, so this is the solar energy harvested over time. So this graph shows the solar energy harvested that is obtained of approximately 0.15 watt hour over 250 hours, because the solar panel will be always receiving energy whenever the energy is present. Okay. Yeah, this is the battery energy levels over time. So you can see we have 10 power banks, which in turn tells us 10 cluster heads. So you can see different graphs. If you can zoom it, then I think you'll be able to analyze better. So it is just showing how the charging and discharging are happening in the power bank, which is inside the cluster head. Yeah, this graph shows the power delivered over time. So we can see that the power is continuously delivered to all the cluster heads within the network. So this is the notification status of the power bank, showing all 10 power banks successfully sent notifications indicating uniform communication and status reporting across the entire network. So we have seen these 4 graphs wherein continuous energy from the solar panel is generated. The charging and discharging of the cluster heads within the network, the linear power which is delivered over time for the entire duration of 250 hours within our simulation environment. And finally, the notifications which is sent by the cluster heads to the energy management system, so that it will say that all the network, the whole network is working in a synchronized fashion and we are delivering efficient data communication. Yes, the conclusion here is, the study proposes a solar-based energy harvesting and management system to ensure continuous operation of underwater sensor nodes using power banks and cluster heads. It can further be extended to multi-source renewable energy harvesting for energy harvesting for enhanced network reliability and sustainability. So multi-source can be acoustic, it can be optical in some cases, and many more, because in underwater environment, the communication medium used was acoustic previously, But the issue with acoustic communication is the data rate is just 1520 meters per second, which is very less, because in underwater environment, the radio frequency attenuate faster. So that is why the research went to acoustic signal. So since the data transmission is very less as informed, next it was evolved to optical communication, but in optical communication, the range, the communication range was less. Now it is magnetic induction. So the solar panels will be having a bigger wires, one connected to one of the cluster head, and the cluster heads will be giving the energy throughout the simulation time. Yeah, that is what I wanted to convey. These are my references, and yeah, thank you. Thank you.
Okay. Thank you, Mr. Yaswat Nancapa, for your interesting presentation. Now we are open for the Q&A session. Okay, please.
Okay, thank you, Professor Reswan. So I think your topic is related with the authors that's in afternoon regarding the power transmission underwater. But maybe you can elaborate more with him. But my question in your topic is because of the sometimes uh, the power from the source is sometimes not continue, and then sometimes it will be disconnect or stop.
True.
So how about the in the charging process in power bank? So it will be affect the lifetime of the power bank or not, or maybe some trouble there.
Yeah,
So
understood
yeah,
the question.
okay.
Thank you, sir.
Thank
Thank
you.
you for the question, and it is a really interesting question. So the thing is, we know that the solar energy is not always there, obvious. But the thing is, since we have this central management system, wherein it will store the energy which is received from the solar system, same like our hot water. So it stores the hot water during the daytime, and we can take out the water at any point of time. So the central management system stores the battery and then delivers it to the cluster heads whenever required. Did I answer your question? No?
Maybe the power bank, how it affect the power
I mean
bank lifetime.
the battery,
Yeah.
because we charge the battery, right?
Hmm.
So if this one stop, so the charging process is stop.
Hmm.
So it will be decreased because it's not really full battery, and then after that it's charging again. So it's make discrete charging and discharging. So it will be decrease the power bank or not, or how to solve this?
I think you are talking about the cluster head battery.
Yes,
Cluster, the battery in the cluster head.
Yes.
Yeah. So since that energy management system continuously delivers the energy and data, both energy and data to the cluster head. So there will be charging. So that is why charging and discharging graph I had shown. So obviously there will be charging and discharging. So whenever the capacity of the battery drains out, then the energy which is stored in the central management system. So central management system is connected to the solar panel, what you are talking about. So that delivers the power. If there is a communication failure, sometimes in networks, obviously communication failure will happen. In that case, that cluster head will be considered as a and form a network. Is it fine, sir, or else I need to elaborate more? Yeah, thank you. Thank you very much. Any other question? Yeah, please.
Thank you for your nice presentation. I have a question about your solar panel type. So, because this is a specific application for underwater, do you have any specific requirement for the type of solar panel that is ideally should be used for underwater application? Because I imagine that the environment will be different from the terrestrial. Okay, thank you.
Yeah. Thank you. Thank you for the question. So the thing is, we are just designing the prototype. we are yet in simulation mode. We have a contact with the Naval Research Board in India. So we are working with them. So we are coming by with a customized solar panel as informed, because there will be harsh environments in water. As of now, if we are testing it in what is that swimming pool in our university. So as of now, we don't see the challenges of water currents, submarine movements, or whatever. So we are just in the prototype mode. We are having a planning to have a customized solar panel in the future. Thank you.
Okay, maybe okay, no, it's okay. One more question.
Thank you, Professor, for a very interesting talk. So I have a question. As far as I understand, please correct me if I'm wrong. You want to deliver the power wirelessly to the nodes of the cluster by magnetic induction. So
Yeah,
how is the
please,
yeah how
please
is the
continue. Please continue. Yeah.
how is the principle?
Initially from the solar panel, which is connected to the central management system, central power management system. So that is delivered with wire, in wire, big cables, because initially we cannot directly send it. The cluster head, the first cluster head will be in the shallow region of the water. So one more option is to deliver the energy via acoustic communication. So, but the acoustic communication is not that much reliable. There might be chances that we might lose some packets of data. If it is energy, then it's fine. Consider I want to deliver 0 0.1 watts of energy, and it is just 0.09 watts, right? So in that case, it is fine. But the data is lost in some cases when we consider acoustic communication. So initially, from the central management system, we give the data or energy via wired mode. Basically, that is the best option. But in the network, it will be wireless. All the cluster heads which are connected. Yes.
Elaborate a little bit how?
We have this mobile phone, right? So the mobile phone will be having the charging cable. So charging cable and the mobile phone are physically connected when we see it with our eyes. But both the cables, that is the cable which we have and the mobile phone, will be having this magnetic induction. I mean to say magnetic field, so that the transmission will happen, energy transmission will happen. Similarly, I gave an example of an electric toothbrush. So you will not see physical communication. It is just placed as a holder, but the magnetic that is what magnetic induction means. So with the help of magnetic field, the energy is passed between those two devices. That is the charging cable and the actual device.
Thank you.
Thank you. Thank you for the question. Thank you. Thank you. Thank you all.
Thank you, sir, for the insightful discussion. So I will continue to the next presenter. I will invite Miss Maris. So she joined online, so we will play her video. I'll call Miss Mariska Regina Christopher Hau from Bina Nusantara University. Okay, the screen is yours.
I've submitted the video, so can you play the video? And real-time laser guidance. Our goal was to develop a portable, and reliable solution to one of the most common and challenging clinical procedures, securing intravenous access. Vein access is a foundational and critical step for many medical interventions, including IV insertion, blood draws, and various surgical procedures. However, locating a suitable vein can be incredibly challenging. This is especially true for patients with difficult venous access or DVA, which includes those with obesity, dehydration, darker skin pigmentation, or pediatric patients with smaller veins. The traditional method in finding veins relies solely on visual inspection and palpation, which is often unreliable and dependent on the nurse or doctor. When this fails, trials, repeated attempts at venipuncture leads to increased patient pain, higher risk of infection, and overall lower procedural success rates. This highlights the urgent need for more reliable, accessible, and non-invasive technologies. Current vein-finding solutions can be costly and lack portability. Our clinical need was simple: to create affordable, reliable, and easy-to-use device to improve patient safety, to address varying clinical needs and resource settings. We developed two distinct prototypes. First is the Simple Vein Finder, which is a low-cost, field-ready device utilizing red LED illumination and a built-in angled needle guide for direct visualization of superficial veins. And the second one is the Advanced Vein Finder. This system integrates near-infrared imaging, or NIR, machine learning segmentation, image enhancement, and a touchscreen selection system with real-time laser guidance. First, I will explain about the simple prototype. The Simple Vein Finder is built for efficiency. It uses 6 high-powered LEDs in the 620 to 725 nanometer wavelength range to penetrate the skin and highlight the veins. The key to its design is a 25-degree built-in angled needle slot, which is the standardized angle of insertion in clinical settings. The device is housed in a 3D printed PLA casing and powered by a rechargeable 3500 mAh battery for full portability. Our validation showed that the prototype is comparable to commercial devices in terms of vein clarity, contrast, and visibility. Its primary limitation is reduced effectiveness for deep veins, darker skin tones, or under bright ambient light. Due to the limitations of the simple vein finder, we decided to make another prototype, which is the Advanced Vein Finder. The Advanced Vein Finder is a compact portable system weighing less than 1 kilogram built around a Raspberry Pi 4 and a 7-inch touchscreen LCD. The workflow is as follows. First is imaging. An array of IR LED illuminates the patient's arm and a Noir camera captures the image. Veins appear dark because they absorb more IR light than surrounding tissue. Next is the processing and segmentation. The image is led to a machine learning model, a modified deep lab V3 convolutional neural network implemented in TensorFlow, which is trained to perform semantic segmentation. It is non-medical, and its role is simply to accurately isolate the arm region from the background with an accuracy of 99.37%. And then, we apply contrast-limited adaptive histogram equalization, or CLAHE, to the segmented image. This image processing technique significantly enhances local contrast, highlighting the subtle vein patterns for the user. And next is selection and marking. The enhanced vein image is then displayed on the touchscreen, and the user simply taps the vein they wish to access. The coordinates of this tap are then mapped to servo angles using a bilinear interpolation algorithm based on a pre-calibrated grid. Finally, an ESP32 microcontroller uses these angles to precisely control a pan tilt servo system that aligns a laser marker with the selected vein location. This system achieves a highly accurate laser marking with an average deviation of just 3 to 5 millimeters, provided the arm is correctly positioned. In conclusion, this study successfully developed two practical vein localization prototypes to overcome the limitations of traditional venipuncture. The simple system offers an affordable, low-cost, and field-ready solution, which is best for superficial veins. And the advanced system delivers better vein view and real-time marking through the integration of NIR imaging, machine learning model, image processing, and laser guidance. Our overall contribution is a scalable, user-friendly tool that directly contributes to safer and more effective venipuncture procedures. Thank you for your time and attention.
Okay, Miss Mariska, thank you for your nice presentation. So now we are open for the Q&A session. Okay. So we are open for the question in both online and offline. Is there any question? So maybe I will start with my question first. So Miss Mariska, you mentioned that the deviation of the, uh, co- if I'm not wrong, so you make two device, right? The two devices, and then you mentioned the deviation of your last device within 3 to 5 millimeters. So do you think that this device is usable for all ages, or it's only certain ages? I mean, like, is it possible to use this device with that deviation for the infant or the babies, for example? And then as I remember, you didn't report the deviation for the first device. Maybe you can also elaborate about this. Thank you.
Okay. Is my voice audible?
Yes, yes, you can.
Yes. Okay.
Yeah.
So for the first device, it is only NIR light based, so there's no deviation. So it just so the light just shines onto the skin, and then you can see the veins clearer because the wavelength of the light allows it to penetrate the skin. So the veins with hemoglobin on it, it will appear darker. So there's no deviation for our first prototype. And for our second prototype, the deviation is actually because of the limitation of our servo, in which we use a 180-degree servo, where, in the future, if you can change the servo, then the deviation will be close to zero. So it should be all right to be used for the infant. But for the prototype right now, I don't think it's very feasible to be directly used on different types of people because the deviation is still there, and the servo that we use is still not that the best one that can be used. Does that answer the question?
Yes. Okay. Thank you.
Okay, thank you.
So for the participant, do you have another question? Maybe in the for the online participant, you can also raise your hand or type your question on the chat box. You mentioned that the deviations may come from for the input give the light to the arm. Where is the distance? So it means that it will deep distance
Sorry, can you
to
repeat the question?
be I mean, like, if you measure with the different distance, the one with camera, the
I'm
one
sorry.
with camera, and then like on that, so you need to adjust the light and also the arm. Miss Mariska?
Wait, sorry, you were disconnected. Can you repeat the question?
Okay, so you need the device with the camera, you need to adjust the distance of the light, the camera to the arm, right? So it means that the result strongly dependent to the distance. And then how is your what is your strategy to adjust the distance to be always the same, like the certain range, and then you to get the standard result? Because like for, I mean, like some people maybe because they have bigger hand, the distance will be very close, but if they have like small hand, it will be very far, and it's difficult to read the result. So what is your strategy to maintain the distance?
Okay, so actually from our mapping, we already considered this. So when the hand appears under the camera, the mapping will try to adjust this to its best ability. But then again, the main issue with the distance and the deviation is in the parameters of the servo that is not flexible enough to reach the grid or the coordinates that we want. Does that answer the question?
What is the maximum distance that can be that readable?
The maximum distance that is reachable by the server right now is an A4 paper.
For
So
paper?
around an A4 paper. A4 paper
Oh.
size. So it's around that rectangle.
Can you maybe like how many centimeters or millimeters?
Okay, I think it's
Specify.
210 millimeters times 297, around that.
Okay. Thank you, Miss Mariska Hao. Thank you for the discussion, and then we'll continue to the next presenter. But before moving to the third presenter, I would like to have a short break. So for the online presenter, please turn on your camera and give your best smile for the photo session. Miss Intan, are you ready? Okay, so we will take a picture for the online presenters and also participants in 3, 2, 1. Okay, again, 3, 2, 1. Okay, and then the last one, 3, 2, 1. Okay, wonderful. Thank you very much, everyone. Now we will move to the next presenter, Mr. Imam Mulyanto from National Research and Innovation Agency.
Good day, everyone. My name is Imam Mulyanto. Thank you. For Photonic, National Research and Innovation Agency, BRIN. Today, I will present our data development of the real-time water level monitoring system using deformable optical fiber sensor and cloud-based dashboard. This research is a collaboration between BRIN and Universitas Negeri Jakarta under the Photonic and Automation Engineering team. Flooding is one of the most destructive and frequent natural disasters, particularly in tropical countries like Indonesia. It causes major damage to infrastructure, loss of property, and disruption to communities every year. Because of this, having a reliable and continuous water level monitoring system is crucial for early warning and rapid response during those events. However, most capacitive sensor and ultrasonic transducers still face serious limitation. They can degrade quickly when exposed to moisture and debris. They are affected by electromagnetic interference, especially in industrial or high voltage environment, and they often fire under extreme weather conditions. To address this problem, we propose the use of fiber optic sensor, particularly based on the macrobanding principle. Fiber optic sensors are immune to electromagnetic noise, corrosion resistant, and capable of high sensitivity even over long distance. These properties make them ideal for use in harsh outdoor environments such as flood monitoring system. The main motivation of this research is to develop a low-cost, real-time, and scalable water level monitoring system that can be easily deployed in flood-prone areas. Our system combines three key technologies. One, deformable optical fiber sensor as the primary sensing element based on macro bending. Two, embedded IoT electronics using Arduino Uno and ESP32 for data processing and wireless transmission. Three, cloud-based dashboard using Firebase to collect, store, and visualize the water level in real time. The objective is to design and test complex monitoring architecture from sensing and data acquisition to cloud transmission and web visualization. We also aim to prepare the system for feature integration with machine learning, which can predict short-term water level trend. Let's move to the methodology. Starting with the system design, the system consists of two main parts. One, the optical fiber sensing unit, along with the data acquisition and microcontroller subsystems. Two, the cloud and database layer and the web-based visualization dashboard. At the heart of the system is the optical sensing module, which operates using the macro bending loss principle. In photonic sensing system, we are converting mechanical displacement into optical attenuation. The optical setup includes 1,300 nanometer laser diode as the light source, chosen for its stability and low absorption in unit air. Directional splitter that divide the beam into part, one going through the sensor fiber and another going through reference fiber. Connector that measure the output of each part. We use a single mode optical fiber that is initially coiled in a circular state. This fiber is connected mechanically to a buoy and a spring mechanism. When the water level rises, the buoy moves upward, pulling the spring and deforming the fiber into a half-light or cardioid state. This deformation increases the bending of the fiber end, consequently increases optical power loss inside the core. In simple terms, the more the fiber bend, the more light is lost, and this loss directly corresponds to the water level. Optical output are detected by high sensitivity photodiode, which convert incident light power into proportional codec signal. The reference channel is critical because it helps cancel out unwanted variation such as temperature drift or laser fluctuation, allowing the system to maintain accuracy even over long operation periods. This makes the sensor robust against external interference, a key requirement for long-term deployment in outdoor flood monitoring. The next part is the electrical and data acquisition subsystem. Here we use two microcontrollers. Arduino Uno handles analog signal processing. It receives voltage signal from both photocollector, performs baseline calibration, calculates normalized difference, and converts them into water level values using a predefined calibration tool. Then, these results are sent serially to the ESP32 famous module, which serves as the IoT gateway. The ESP32 connects to a local Wi-Fi network and transmits the data to a Firebase real-time database in the cloud. Firebase was chosen because it supports real-time synchronization and is simple to integrate with web interface. Once the data is stored in the cloud, it can be accessed from any device, a smartphone, tablet, or desktop computer using the web dashboard that we designed. We tested the prototype system in our laboratory, focusing on two key aspects. One, the optical response of the sensor, and two, the performance of the complete IoT monitoring system. For the optical characterization, the sensor was tested for water level between 0 and 150 centimeters. The results showed two distinct response regions. In the 0 to 50 centimeter means the optical power actually increases slightly before decreasing. This was caused by the geometric transition of the fiber from tubular to half staple to pitch, where tension from the spring temporarily improved like guidance. Beyond 50 centimeter, the sensor exhibits a clear and linear decrease in optical power as the water vapor increases. This behavior aligns perfectly with the expected macro-bending attenuation model. From the calibration data, we obtained a slope of minus 0.4434 microwatt per centimeter and a correlation coefficient of R square equal 0.x542, indicating strong linearity and repeatability. Although the test was limited to 120 centimeters due to the tank size, this linear region can be extrapolated to 3 meters for field application. This means the sector can provide both early warning in the non-linear region and accurate quantitative measurement in the linear region. For the system level test, the Arduino ESP32 combination successfully transmitted data continuously through the 5-days flow with an average latency of around 200 to 300 milliseconds, which is fast enough for near real-time monitoring. The dashboard is built to be simple and informative. It displays the current water level, the status classification, tip, alert, or data, and a trend graph showing the daily water level variation. This way, local authorities or disaster management team can see real-time update and make action immediately. The system architecture also allows for multi-site monitoring, meaning several sensors in different location can send data simultaneously to the same truth dashboard. The dashboard correctly displays live reading and update the colorful status indicators in real time during continuous operation. System uptime reaches 98%, showing that the hardware and communication link are available. To conclude, we have successfully developed the real-time water level monitoring system that integrated deformable optical fiber sensing, embedded IoT hardware, and broad visualization. The system shows good linearity, stable operation, and reliable wireless data transmission. It provides a promising foundation for low-cost, variable flood monitoring able in vulnerable region. In the future, by adding machine learning forecasting, we expect to transform the system from just a monitoring tool into a smart early warning platform for flood risk management. Thank you very much for your attention. Good day, everyone. My name is Imam Mulyanto from Research Center for Photonic, National Research and Innovation Agency.
Okay, thank you, Mr. Imam, for the interesting presentation. Now we are moving to the Q&A session. I'll invite all participants from online and offline to ask questions. You can raise your hand or type your question on the chat box. Okay, maybe I'll start first with my question. So, Mr. Imam, to show us the power loss of the device in like
Yes. Can we repeat this transmission trouble?
But sorry.
Wi-Fi trouble, no clear.
Okay, so you show the power loss graph. Maybe which slide? I cannot remember which slide is that. So you show the power loss of the when you measure the optical power loss. So the optical power loss, the optical power will gradually decrease as the water level become higher. Like for example, you show like for 150 centimeters. So monitoring of the power loss. So I'm just wondering that this slide. So I just wondering that just this maybe the 3 meters, does it the maximum the deep level of the water that this device can be can measured? Or and then if it's yes, then maybe my next question is like, what is the strategy to make the range is become deeper? Maybe that's my question. Did you get my question, Mr. Imam?
Okay. Power loss range 0 to uh, to 160 uh, 100 0 so 6 micrometer. This is decrease.
Yes, yes. So I'm just imagine that within 150 centimeters, the power, like the optical powers is already 50 micron, 50 micron watts. So I'm just wondering that maybe if we go deeper, like up to 3 meters or 300 centimeters, it will reach to zero, or I don't know, like maybe you can explain like what is the maximum power loss before what is the maximum distance become the power loss become zero?
Tingginya itu maksimum meter. So
Mr. Imam, you can also answer in bahasa Indonesia.
Jadi maksimum distance tingginya 3 meter. Terus penurunan dari power laser diodenya dari 105 sampai 60 mikrowatt itu penurunannya. Jadi maksudnya makin tinggi level airnya, makin dari laser dietnya itu. Dari 120 mikrowatt totalnya menjadi kalau sampai 3 ke atas itu jadi berapa? Power loss-nya jadi iya dari 110 mikrowatt hingga 60 mikrowatt itu gradiennya itu kemiringannya.
Ya, baik Pak, dimengerti. Izin bertanya untuk level air yang lebih dari 150 cm, apakah ada datanya Bapak Punten?
Oh, no data.
Oke, berarti the maximum measurement is in 150 ya, 150 cm ya?
No, fear. in this
Okay.
in this graph. Yeah.
Okay, so the optical power tends to decrease as the water level become higher. So I understand. Okay, thank you very much, Mr. Imam, for the interesting discussion. And then we will move to the next offline presenter. I will invite Miss Tasya Gian Pavita from Universitas Pendidikan Indonesia.
Thank you.
The floor is, okay, the floor is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. My name is Tasya Gian Pavita from Universitas Pendidikan Indonesia. And today presentation, I will present to you about the research with the title is Tuning PVA Molecular Weight for Structure Property Optimization in Piezoresistive Hydrogel-Based Flexible Sensor. And the first is and the first is the background. There is a wearable sensor technology is rapidly advancing in various fields such as healthcare and sports. But it is generally made of metals or synthetic polymers that pollute the environment and are not often biocompatible. And these metals or synthetic polymer makes environmental pollution, allergic reaction, and low flexibility too. Because of that limitation, we propose the PVA-based hydrogel. And why hydrogel? Because hydrogel have 3D macromolecular network that is hydrophilic, capable significantly absorbing water and possess flexibility, making them suitable for application in wearable sensor. And this study is to develop a piezoresistive eco-friendly hydrogel, where is resistant change due to deformation that alters the electrical conduction pathways within the materials. And next is the research aim and overview. The materials that we use is PVA, boron as crosslinker, and multi-walled carbon nanotube as conductive filler. And we developed the PVA-based hydrogel for wearable sensor. And then for the stage 1, we optimize the PVA molecular weight. There is 61, 70, 145, and 200 kDa using the key parameters. There is swelling ratio, water contact angle, and then the tensile test. And then for the stage 2, incorporating multi-walled carbon nanotube to the PVA hydrogel to study piezoelectric performance. And then we develop a flexible and eco-friendly wearable strength sensor using PVA based hydrogel. And next, hydrogel. The first parameter is the swelling ratio. Is crucial as it will network and the increasing molecular weight. In here, we can see the increasing molecular weight, increased network density and crystallinity, and then max reducing spheric, while molecular weight hydrogel are stronger but absorb less water. And the second parameter is the water contact angle. Water contact angle analysis in here surface hydrodensity of the hydrogel composite. And as you can see in here, the PVA1 lows water contact angle due to field orientation on the surface, indicating higher surface hydrophilicity. And next is the tensile strength. It is used to evaluate the mechanical durability and flexibility required for wearable sensor application. In the table, we can see that mechanical strength increased with higher PVA molecular weight. In here, we can see elongation. And for the PVA with 145 kDa, had the balanced strength and flexibility. With higher molecular weight, forms a denser entanglement, improving load-bearing ability. And next, we add the CNT as conductive filler to the hydrogel PVA composite. In here, we use the same variation of the molecular weight. And the first parameter is the swelling ratio. As we can see in here, the PVA CNT with 145 kDa show the highest swelling among CNT containing sample. And the 145 kDa network allow good CNT dispersion and maintain porosity for water absorption. And next is water contact angle. The CNT addition significantly affected surface hydrophilicity. As you can see in the figure in here, the PVA CNT 145 maintain low water contact angle that indicating uniform CNT dispersion and good hydrophilicity. And for proper dispersion in 145 kDa, improve mechanical strength and load transfer. And the balanced hydrophilicity is essential for flexible sensor to maintain ion mobility, comfort, and stability of the hydrogel sensor. And then for the tensile strength, as you can see in the table, that CNT addition made performance depending on the PVA molecular weight. As we can see, that PVA CNT 145 kDa achieved the best strength and elongation with no fracture in analysis. Because the good CNT dispersion enable effective load transfer. And based on the swelling ratio, water contact angle, and the tensile strength result, we can see that PVA CNT 145 achieve balanced swelling, providing softness, flexibility, and ion mobility essential for a sensor performance. And next is the characteristics. First, we use the phase hydrogen bonding in PVA network and the cross-linking, the successful cross-linking. In here, we can see that there is a BOC stretching at wave number 1142. It means the cross-linking between boron and PVA. Based on the Fourier transfer infrared result, confirm that boron effectively cross-link PVA, while CNT incorporation introduced additional intermolecular interaction that strengthen the hydrogel network and enhance its mechanical properties. And the morphology characterization, we use SEM cross-section. As we can see in the figure A and B, hydrogen. Sorry. And in here, for the PVA CNT 200, kDa has the highest conductivity because its dense network improves CNT contact and charge transport. And for the PVA CNT with 145 kDa, show the lowest conductivity compact matrix because the compact matrix isolates CNT and reducing pathways. And next is performance of the hydrogel sensor. We use the strain stress sensor analysis. We use the tools is universal testing machine. We use the uniaxial tension with relative resistance change to analyze piezoresistive behavior. In the graph, we can see that there is a PVA CNT with 61 kDa has the moderate tensile and stable but less entangled PVA CNT network. And for the PVA CNT 70 has the weakest tensile and the hydrogel is early fracture. And for the PVA CNT with 145 kDa has the best mechanical strength, as we can see in here, with flexible deformation. And it has stable resistance response too. And the PVA CNT with 145 kDa has good balance of strength and stability. And for the PVA CNT with 200 kDa, the hydrogel was brittle, fails quickly after 16 kilopascal, and the hydrogel is rigid too. Because of that, the hydrogel is less suitable for dynamic sensing. And the performance of the hydrogel sensor, we use the LED lamp to check the conductivity of the hydrogel. In here, we use the LED connected to PVA CNT hydrogel to visualize conductivity under tensile strength from 0 to 100%. And we use the PVA CNT 145, as I mentioned before, because it's the most balanced and it provided good mechanical strength, stable conductivity, and flexible which are essential characteristic for, and as we can see, transmission. And in here, in PVA hydrogel, as we can see, there is no LED illumination at any strength because it's no conductive pathways and confirming non-conductive nature of PVA hydrogel. And based on the test result, we can conclude that PVA CNT hydrogel show a clear piezoresistive response where mechanical deformation directly affects electrical conductivity. And then, based on study, we can conclude that the optimal composition was achieved with PVA CNT hydrogel containing 145 kDa PVA. And this formulation provided a balanced combination of mechanical strength, hydrophilicity, swelling capacity, and electrical responsiveness. And demonstrate stable and linear signal output. And the hydrogel maintains softness and flexibility, essential for wearable application. And therefore, the PVA CNT with 145 kDa is identified as the most suitable candidate for flexible and durable wearable strength sensor development. That's all from me. Thank you, and I will thank to research assistant scam from BRIN and riset kolaborasi internasional from Universitas Pendidikan Indonesia to support this project. Thank you.
Okay, thank you, Ms. Tasya again, Pavita. So we already have one question from the chat box. So let me read the question. So it's from Ms. Tiara from Esa Unggul University. So the question is, how does this hydrogel behave under strain during sensing? Okay.
Okay. As I mentioned before, that the hydrogel sensing mechanism is piezoresistive. Piezoresistive, and when we give strength to the CNT network in hydrogel will partially unconnected, or I mean disconnected, and it gives the higher resistance. Because the piezoresistive hydrogel is the principle of the piezoresistive hydrogel is resistant change due to deformation that alters the electrical conduction pathways within the material.
Okay,
Maybe that's all.
is that answer your question, Miss Tiara Putri? Or maybe I have one additional question. So because you already mentioned like how the hydrogel works as the sensing, so maybe can you go back to the LED, the last, yeah, because in the PVA hydrogel, we cannot see the light of the LED, right? So I assume that it is insulator. So when you try to add the CNT, then it become, I don't know, is it semiconductor or conductor? I don't know, like, and then maybe you can give like the mechanism, like the probable mechanism of the electron, because the electron move from the one probe to the another probe, right? So maybe you can try to elaborate about the probable mechanism of the electron mobility. Thank you.
Bagian yang so in the hydrogel with CNT in here, we can see that in initial stage that LED is bright. Is bright brightness of the LED, and in here the mechanism is because the CNT in the hydrogel, when it give strength to the hydrogel, the CNT molecular partially unconnected or separated to the CNT partially unconnected, and then when the hydrogel is back to the initial stage, the CNT will back to the first place, and it give the brightness of the LED, and the brightness LED will decrease because there is a resistance when the CNT partially move to other place or unconnected. Maybe that's all.
Okay. Okay, please.
Assalamualaikum warahmatullahi wabarakatuh. Hello, my name is Priyo. I'm from Research Center for Telecommunication. My passion work is in wearable device or RF device. I would like to have a question about you are here in comparing with the 4 type of PVA, right? I mean, and then you measure it and you put the camera in the point, and it's directly in the center of the substrate, or just and measuring the hydrophilic or hydrophobic on that. And then the question is, because you mentioned that this is going to be wearable device, let's just say we assume we are going to be wearing it, and then you are going to be sweating, and then the device itself going to be absorbs the sweat, I mean, and then the dimension going to be stretch. I mean, dimension is going to be expand. So is it a resulting the conductivity or adding the resistivity? Yeah, that was the question. Thank you.
Thank you.
Maybe if the hydrogel absorbing the sweat, it will give it will make adding the resistivity, no conductivity, because the conductivity in this study, the conductivity is from is from multi-wall carbon nanotubes, and
That's all. Maybe you can highlight about the size deformation. I mean, like the hydrophilicity is correspond to the swelling, right? When it hydrophil, then it become easier to swell, like the swelling. It become bigger when it contacted to the water. So what his question is, if it contacted to the sweat, maybe the size is will be larger, melar in bahasa. Yeah. So will it affect the will it affect the performance of your device?
Uh, when the hydrogel is bigger than initial stage, the effect is maybe the resistivity will increase because the size of the hydrogel is increased. And for this study, we not yet study the hydrogel based on sweat because we study the swelling ratio to see the hydrogel. Oh, jadi maaf, saya menggunakan bahasa Indonesia. Jadi di proyek ini saya belum mengujinya jadi untuk swelling rasio di sini itu untuk menguji ketahanan hidrogel di di kondisi yang berair. Nah, untuk akibat adanya keringat itu mungkin bisa meningkatkan mungkin bisa mengganggu resistivity dari si hydrogel dan tidak berpengaruh terhadap conductivity-nya karena conductivity di sini dihasilkan dari multi-walled carbon nanotube itu sendiri. Jadi mungkin begitu jawaban.
Okay. So maybe we'll have last question from the chat box. It's from Miss Clarissa. Why this? Yeah. So she's asking about your why you choose to focus on the molecular weight optimization, like this parameter. Why you choose this parameter to be varied?
The parameter molecular weight is choose because the molecular weight affect to PVA crystallinity, texture of the hydrogel sensor, flexibility, and cross-linking density. And for as we can see, for the increase molecular weight that affected to the texture hydrogel for example, in 200 kDa hydrogel, the texture is rigid and very fracture, and so we can achieve the optimal composition with tuning the PVA molecular weight to achieve the best composition for wearable sensor.
Okay, so the molecular weight will affect the mechanical overall properties, right? Okay. Thank you very much, Miss Tasia, for your interesting discussion. Okay, thank you very much. Now we will moving to the next presenter. I'll invite Miss Crescentiana Katlea Jesiana from Institute 10 November Indonesia. Okay, the floor is yours.
Okay, thank you for the opportunities. Good morning, everyone. My name is Crescentiana Katlea Jesiana from 10 November Institute of Technology. Today, I'm honored to present our research titled Development of Zinc Oxide-Based UV Detector Devices as a Wearable UV Index Monitor. First of all, the outline of this presentation include introduction, methodology, design experiments, results, and conclusion. First, ultraviolet or UV radiation is both beneficial and harmful to human bodies. In moderate amount, it helps our bodies synthesize with vitamin D. However, excessive exposure causes skin damage, premature aging, and even cancer. So, based on these cases, highlights the needs for a simple and reliable wearable UV monitoring system that can help people stay aware to the real-time UV intensity. In this work, zinc oxide was selected as the active sensing material because it is a wide bandgap semiconductor with 3.37 electron volt and its high sensitivity to UV light, low cost, non-toxicity, and design flexibility make it ideal for the optoelectronic sensors. Meanwhile, polyimide or PI was chosen as the flexible substrate due to its excellent flexibility, heat resistance, lightweight, and suitable for portable applications. Previous studies have explored several configurations on zinc oxide-based photodetector on a flexible substrate. Singh et al. 2023 have fabricated the zinc oxide-based photodetector with the magnetron sputtering technique and analyze the performance under piezophototronic effect. And the weakness of these studies is vacuum deposited, slow response time, and high cost. And the other studies have explored and have developed zinc oxide polyimide photodetector with the spin coating method and analyze and observe the how film thickness affect the optical response and mechanical stability. And however, most studies focus only on device characterization with limited attention to the system integration for real-time and wearable UV monitoring. Therefore, the main goal of this work is to fabricate and integrate a zinc oxide-based UV photodetector on a flexible polyimide substrate as wearable UV index monitoring device. And the methodology of this research consists of two main stages. The first stage, device fabrication, where we fabricate the zinc oxide-based photodetector with the spin coating method and on a flexible polyimide substrate, where the spin coating allows the zinc oxide solution to spread uniformly over the surface through high-speed rotation and creating a consistent and high-quality zinc oxide film, and then followed by characterization of UV photodetector devices. And the second stage is system development, where the fabricated devices was integrated with the electronic circuit and the microcontroller to form a wearable UV index monitoring system. And then in this stage, we use transimpedance amplifier or TIA, which converts the small photocurrent that produced by the photodetector into the readable voltage signal for processing and display. Next, for design and experiment, for device fabrication process, begin with the substrate preparation and then preparing the zinc oxide gel solution using zinc acetate dihydrate, monoethanolamine, and 2-methoxyethanol, stirred at 60 degrees Celsius for 3 hours. And then the solid gel solution was spin coated at 1000 RPM for 30 seconds, and then followed by preheating at 170 degrees Celsius for 5 minutes. And the procedure from spin coating into the preheating repeated for 10 times, and then followed by the post-heating at 170 degrees Celsius for 30 minutes. And finally, the silver interdigited electrode was deposited with the metal evaporation to form a metal semiconductor metal structure, and this process resulted flexible and functional zinc oxide photodetector. And for characterization setup, the characterization was performed to evaluate the optical and electrical performance of the device. First, UV spectroscopy was used to determine the absorption spectrum and calculate the bandgap energy of the zinc oxide film, and then the electrical characterization was measured using Catley measurement system under dark UV illumination and bending condition to observe the current voltage behavior and mechanical stability. And for the response time was measured using oscilloscope under UV light and with the pulse voltage bias to observe how quickly the device responds to the UV intensity changes. And for system design and integration, in this stage, the fabricated photodetector was integrated with the electronic system where begin with defining the electronic component pinout design, which connects the UV photodetector with the MCP602 op-amp-based transimpedance amplifier, and with the Arduino Nano microcontroller, OLED display, lithium polymer battery with a step-up converter. And for the Arduino codes, performs analog to digital conversion and applies the calibration equation and also display the UV index on the OLED screen, and the LED indicator lights up whenever the UV index reach high index. And after the circuit design, all the layout implemented on the printed circuit board or PCB, and followed by programming and components installation. And finally, all the entire system were enclosed in the 3D printed case by designing portability and comfort in wearable applications. And for the result, application characterization result showed that zinc oxide layer exhibits strong absorption at the wavelength of near 360 nanometers, and it's indicating sensitivity on the UVA region, and the bandgap energy is calculated at 3.275 electron volt, which confirming it's a high quality zinc oxide film. Additionally, zinc oxide on polyimide absorption slightly extends the absorption into the visible region, suggesting the potential on multispectral sensing applications. And for the electrical characterization results, the current voltage characteristic produce linear symmetrical nonlinear curve, and with the threshold voltage around 0.1 volts, and with the dark current measured at 0.142 microamperes, while the photocurrent reached 5.08 microamperes under UV light and 70.33 microamperes under room light. And when bent, the performance decreased to 33.58 nanoamperes, which confirming mechanical strain sensitivity. And for the response time test showed a rise time of 0.33 milliseconds and a fall time of 0.34 milliseconds, which confirming rapid response, which is suitable for real-time monitoring. And for the calibration results, the system was calibrated using WHO UV index data, and the data collected in Surabaya, and it's got the linear regression graph and also the linear regression equation as showed in the slide, and got the R square equals 0.969, which indicating 96.9% correlation between the device output with the reference values. And after that, the equation was embedded in the microcontroller codes to allowing automatic and accurate UV index conversion in real time. And after all the integration, all the component was assembled in the printed circuit board or PCB, and also enclosed in the 3D printed watch-like case. And for the field testing was performed in June 2025, and it showed the strong agreement with the WHO UV index data, where we get the UVI 7 at noon categorized as high, and UVI 1 at 4 p.m. categorized as low, UVI 0 at 5 p.m. also categorized as low, which indicates the device effectively tracks the UV index and UV exposure in real time. And in conclusion, zinc oxide-based UV detector was successfully fabricated on the flexible polyimide substrate with silver interdigitated electrodes, forming a metal semiconductor metal structure. And then UV-Vis results showed strong absorbance in the UVA region with a band gap of 3.275 electron volt, confirming high optical quality. And the device exhibited a dark current of 0.142 microamperes, photocurrent of 5.08 microamperes, and a fast response with a rise time of 0.83 millisecond and a fall time of 0.34 millisecond. The device is integrated as a wearable UV index monitor capable of detecting UV rays, converting them into an electrical current, then amplifying and reading them with a microcontroller to display a UV index value and provide a visual warning. Calibration with the WHO reference achieved a strong linear correlation and 96.9% accuracy. The system shows high sensitivity and reliability. The performance degradation occurs after repeated use due to zinc oxide and silver layer damage, suggesting the need for encapsulation and material reinforcement. Okay, wait. Okay, thank you for your kind attention. That will be all from me. I apologize if there were any mistake or shortcomings. I'm glad to answer all the questions you might have. Thank you.
So now we are moving to the next presenter. Thank you very much for your presentation, Ms. Katlea. Now we open the Q&A session. I will place the to all participants. Okay, Mr. Wilman.
Thank you for a nice presentation. So I have two questions. The first one, because you're using flexible and then you're using spin coating, how to make sure your coating is even because you spin it? So how thick also your polyimide? And the second question is that, I'm curious, what is the state of the art, I mean globally, for this type of UV sensor using zinc oxide? And do you have a gap with the state of the art right now, or you already happy with the result? Yeah, thank you.
Okay, thank you for asking. Maybe I'm sorry if I've not mentioned for the spin coating process. So, yeah, because I use the polyimide substrate as the flexible substrate, and it's have a thin or a flexible. So for the spin coating process, firstly I use the glass substrate as the base. So the polyimide substrate um I dig into the glass substrate, so it made the substrate more rigid for the spin coating process. Okay, maybe for the second question, mungkin sorry, I try to answer as I know. So the gap for this technology or for this research, so far I already I'm already happy or already for this result because I have reached my main goal is to integrate this photodetector into the wearable system integration. But in the testing, sometimes I face many problem like the absorption for this device maybe have a long or wide absorption for the UV light and also for the visible light. So more improvement is needed for this research, like explore another method or another substrate material. Maybe that's all from me.
Maybe you can add about the uniformity because Mr. Wilman also asked when you do the spin coating, somehow the deposition is uneven. So it's only thick in one part and then the other part is thinner. So maybe you can try to explore like the strategy to make it even, like the whole substrate. the uniformity of the deposit ZNO deposited on the PI substrate. Uniform or not?
Oh, okay. Okay. Overall, the uniformity, because the rotation speed that we use is one 1000 RPM. It's enough for the uniformity. But in each part there is yeah, there is a bubble that um uh compete in one side, but maybe we can improve it by make it the rotation higher, the rotation speed is higher or bigger. Maybe that's all.
You want to highlight that to you need to add the more additional question on the more additional experiment on the spin coater parameters optimization to achieve the uniform thickness, film thickness, maybe something like that. Okay, thank you very much. So we are also open for the next question. Is there any question from the audience or participants online or offline? Okay, maybe I will have one short question. So because you are aimed to create wearable system, so now you are creating wearable sensor device, but the system like the PCB and etc. is not wearable yet. So what is your strategy to make it like wearable device like we already know now? For example, like the smartwatch, something like that. So what is your strategy to make it like go far to make it all from the components also wearable and flexible maybe? Thank you.
Okay, thank you for asking. So, for make this wearable system is more wearable, I suggest to use a smaller microcontroller maybe, and also more. I recommend also to use data logging to collect the long-term UVI data, and some maybe we can control or monitor the UVI not only using the wearable watch. We can also monitor it using our smartphone. Maybe that's all for the future work recommendation for me. Okay.
Okay, thank you very much. So maybe that's all for this session. Thank you very much, Miss Katlea. Thank you for your interesting discussion. So now let's conclude our session for today on the parallel session 6 on electronic materials, components and circuit. And I'd like to sincerely thank all presenters and participants for this insightful discussion. So and then thank you again and I wish you have enjoyable continuation of the conference. See you and wassalamualaikum warahmatullahi wabarakatuh.
Recording stopped.
Thank you, Dr. Diki Punawati, and also thank you for all presenters and participants for the active participation for these parallel sessions. So now we've come to the lunch break, but I would like to announce you of the new schedule, because if you see from the website and the program book that the next parallel sessions will begin at 12:45 UTC plus 7, but the change of schedule that we changed it into 1 p.m. So please be minded that we will continue at 1 p.m. So the same as yesterday, the lunch will be held situated at the Swiss Bell Kitchen Restaurant. So for whoever of you that who just joined the ICRAMET on the second day, that you can use the lift using the lift over there and go to the lobby. And if you can't find the location, please ask the Swiss Bell Hotel staff about the kitchen resto. And also, I would like to remind you, before you going to the lunch, please visit our exhibition booth. So we have from the Roda and Swartz, So for those of you who are interested in antenna testing, radio frequency testing, and material characterization, you can go to the Rohde and Schwarz exhibition booth to the left of the door. And you can ask Mr. Taufan Pega and his teams. So they have the equipment like the vector network analyzer and also the MX05 digital oscilloscope. And we also have to the left from the corridor, we have Patenics Lab. So for those of you who are interested in the area of photonic, chip testing, material characterization, and also battery testing, you can go to Dix Lab booth and you can find Mr. Rehan and team. They are, their area is in the low power system that needs source, measure, and control. Also to the right, on the corridor, next to the right door, we have Bank Rakyat Indonesia. And we also have a exhibition from the Research Center for Electronics of the thermoelectrics, supercapacitor, and biosensor if you want to view them. Thank you. So please come back at 1 p.m.
The current problem in the semiconductor industry testing for the chip is because the current equipment is bulky, expensive, and also not integrated. Our solution provides technology that's 20 times smaller, 3 times cheaper, all integrated with easy-to-use software. Our device analyzing the reliability of the chip. This reduces the amount of defective chips and also puts out high yield in the manufacturing. It is important for the semiconductor chip manufacturers. So we have shipped our product to over 15 countries. Now also being used to different applications such as the AI, quantum, and also in data centers. NASA used for the space, the Army for defense, and the NVIDIA for the AI. For those companies, they use our equipment to be integrated with their chips to make it function properly in different applications. One of the best functions of our product is provide the voltage control. Our equipment helps guide light so it can work properly into different applications. We are inspired to create more innovative devices so we can help people to have a better life around the world. This motivates our team every day.
Making accurate antenna measurements in large chambers and outdoor antenna test ranges, or making long-distance measurements such as testing long cable runs on aircrafts or ships are not easy tasks. The traditional measurement solution uses a 2-port benchtop vector network analyzer. a VNA, where the user must attach two very long test port cables. The problem with this solution is that long cables introduce signal loss, reducing dynamic range. To overcome this challenge, a high-end VNA is required, and components such as low-noise amplifiers are introduced to improve dynamic range. As the frequency of interest goes higher, however, small movements in the test port cables have an adverse effect on signal phase. Introducing the solution to long-distance S-parameter measurement problems, the Inritsu Shockline ME7869A. This modular two-port distributed VNA can make vector-corrected S-parameter measurements over distances as long as 100 meters. Complicated test setups and lossy cables are eliminated, since the instruments are powered by Inritsu's patented phase-link technology. This technology allows synchronization between the two VNA test ports using optical cables. No matter how much the user moves the cables, there's no phase deviation, while system dynamic range is fully preserved no matter the distance between test ports. Now you can confidently test long cable runs from aircraft's nose to tail and wingtip to wingtip, from ship's antennas to underdeck control rooms and antennas on outdoor test ranges, or in large anechoic chambers, all to full performance with a compact and easy-to-use solution. Inritsu, providing excellence in wave measurements, covering the distance with our patented phase-link technology, integrated into the Shockline ME7869A modular vector network analyzer. Inritsu, advancing beyond. Research is our strength to We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare, BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with two main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, it enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An area consisting of research laboratory facilities, testing laboratories, SMEs, tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045, by consolidating science and technology resources and creating a resource ecosystem and research-based economical foundation. Transforming Indonesia as a global reference in the development and application of science and technology, practices, and the good of humankind. Nature is the source of inspiration. Knowledge is the foundation, and to be put in praxis for the sake of the nation.
Over 100 years ago, the discovery of radio waves marked the start of a new era. At that time, our founders Lothar Rode and Hermann Schwarz were still at school. Abilities it offered. A Pioneering scientific spirit and entrepreneurial courage have always been the foundation for the success of Roda and Schwarz. Making ideas real and striving for excellence. The spirit and mindset of our founders live on today and continue to evolve from one generation to the next. Every day, thousands of employees worldwide benefit from the knowledge that is accumulated in our company over decades. At Roda and Schwarz, they learn from each other, showing respect for that which came before them. We're part of this world and pass on our knowledge by providing the best possible solutions and systems. We've never made a secret of our innovation culture. At Roda, hand in hand. We make a difference. Driven by our distinctive passion for technology, we create the innovations that are highly relevant for a safer and connected world. Our customers and partners know they can always rely on us to deliver the highest quality. We are strongly positioned and look forward to a successful future. Our mission is clear. Make ideas real. Yesterday, today, and tomorrow.
Long-distance measurements, such as testing long cable runs on aircrafts or ships, are not easy tasks. The traditional measurement solution uses a two-port benchtop vector network analyzer, a VNA, where the user must attach two very long test port cables. The problem with this solution is that long cables introduce signal loss, reducing dynamic range. To overcome this challenge, a high-end VNA is required, and components such as low-noise amplifiers are introduced to improve dynamic range. As the frequency of interest goes higher, however, small movements in the test port cables have an adverse effect on signal phase. Introducing the solution to long-distance S-parameter measurement problems, the Inritsu Shockline ME7869A. This modular two-port distributed VNA can make vector-corrected S-parameter measurements over distances as long as 100 meters. Complicated test setups and lossy cables are eliminated, since the instruments are powered by Inritsu's patented phase-link technology. This technology allows synchronization between the two VNA test ports using optical cables. No matter how much the user moves the cables, there's no phase deviation, while system dynamic range is fully preserved no matter the distance between test ports. Now you can confidently test long cable runs from aircraft's nose to tail and tip to wingtip, from ship's antennas to underdeck control rooms, and antennas on outdoor test range large anechoic chambers, all to full performance with a compact and easy-to-use solution. Inritsu, providing excellence in wave measurements, covering the distance with our patented phase-link technology, integrated into the Shockline ME7869A modular vector network analyzer. Inritsu, advancing beyond.
Our product is called XDEC, which consists of hardware and software that we created in-house. We integrate our device with the semiconductor chip industry to help them reduce their cost for testing and get more reliable and also high yield of their product. The current problem in the semiconductor industry is that simple. Our solution provides technology that's 20 times smaller, 3 times cheaper to software. Our device analyzing the reliability of the chip. This reduces the amount of defective chips and also puts out high yield in the manufacturing. It is important for the semiconductor chip manufacturers. So we have shipped our product to over 15 countries. Now also being used to different applications such as the AI, quantum, and also in data centers. NASA used for the space, US Army for defense, and the NVIDIA for the AI. For those companies, they use our equipment to be integrated with their chips to make it function properly in different applications. One of the best functions of our product is provide the voltage and current. Our equipment helps guide light so it can work properly into different applications. We are inspired to create more innovative devices so we can help people to have a better life around the world. This motivates our team every day.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Socials, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with 2 main targets. BRIN realizes realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs, tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045 by consolidating science and technology resources and creating a resource ecosystem and research-based economical foundation. Transforming Indonesia as a global reference in the development and application of science and technology practices and the good of humankind. Nature is the source of inspiration. Knowledge is the foundation, and to be put in praxis for the sake of the nation.
Over 100 years ago, the discovery of radio waves marked the start of a new era. At that time, our founders Lothar Rode and Hermann Schwarz were still at school. They were immediately fascinated by this new technology and driven by a curiosity about the unprecedented possibilities it offered. A pioneering scientific spirit and entrepreneurial courage have always been the foundation for the success of Rode and Schwarz. Making ideas real and striving for excellence. The spirit and mindset of our founders live on today and continue to evolve from one generation to the next. Every day, thousands of employees worldwide benefit from the knowledge that is accumulated in our company over decades. At Roda and Schwartz, they learn from each other, showing respect for that which came before them. We're part of this world and pass on our knowledge by providing the best possible solutions and systems. We've never made a secret of our innovation culture. At Roda and Schwartz, excellent development performance and entrepreneurial behavior go hand in hand. We make a difference. Driven by our distinctive passion for technology, we create the innovations that are highly relevant for a safer and connected world. Our customers and partners know they can always rely on us to deliver the highest quality. We are strongly positioned and look forward to a successful future. Our mission is clear: make ideas real. Yesterday, today, and tomorrow.
Making accurate antenna measurements in large chambers and outdoor antenna test ranges, or making long-distance measurements such as testing long cable runs on aircrafts or ships are not easy tasks. The traditional measurement solution uses a two-port benchtop vector network analyzer, a VNA, where the user must attach two very long test port cables. The problem with this solution is that long cables introduce signal loss, reducing dynamic range. To overcome this challenge, a high-end VNA is required, and components such as low-noise amplifiers are introduced to improve dynamic range. As the frequency of interest goes higher, however, small movements in the test port cables have an adverse effect on signal phase. Introducing the solution to long-distance S-parameter measurement problems, the Inritsu Shockline ME7869A. This modular two-port distributed VNA can make vector-corrected S-parameter measurements over distances as long as 100 meters. Complicated test setups and lossy cables are eliminated, since the instruments are powered by Inritsu's patented phase-link technology. This technology allows synchronization between the two VNA test ports using optical cables. No matter how much the user moves the cables, there's no phase deviation, while system dynamic range is fully preserved no matter the distance between test ports. Now you can confidently test long cable runs from aircraft's nose to tail and wingtip to wingtip, from ship's antennas to underdeck control rooms and antennas on outdoor test ranges, or in large anechoic chambers, all to full performance with a compact and easy-to-use solution. Inritsu, providing excellence in wave measurements, covering the distance with our patented phase-link technology, integrated into the Shockline ME7869A modular vector network analyzer. Inritsu, advancing beyond.
Our product is called XDEC, which consists of hardware and software that we created in-house. We integrate our device with the semiconductor chip industry to help them reduce their cost for testing and get more reliable and also high yield of their product. The current problem in the semiconductor industry testing for the chip is because the current equipment is bulky, expensive, and also not integrated. Our solution provides technology that's 20 times smaller, 3 times cheaper, all integrated with easy-to-use software. our device analyzing the reliability of the chip. This reduces the amount of defective chips and also puts out high yield in the manufacturing. It is important for the semiconductor chip manufacturers. So we have shipped our product to over 15 countries. Now also being used to different applications such as the AI, quantum, and also in data centers. NASA used for the space, the US Army for defense, and the NVIDIA for the AI. For those companies, they use our equipment to be integrated with their chips to make it function properly in different applications. One of the best functions of our product is provide the voltage and current. Our equipment helps guide light so it can work properly into different applications. We are inspired to create more innovative devices so we can help people to have a better life around the world. This motivates our team every day.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with 2 main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs, tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045 by consolidating science and technology resources and creating a resource ecosystem and research-based economical foundation. Transforming Indonesia as a global reference in the development and application of science and technology, practices, and the good of humankind. Nature is the source of inspiration. Knowledge is the foundation, and to be put in praxis for the sake of the nation.
Over 100 years ago, the discovery of radio waves marked the start of a new era. At that time, our founders Lothar Rode and Hermann Schwarz were still at school. They were immediately fascinated by this new technology and driven by a curiosity about the unprecedented possibilities it offered. Pioneering scientific spirit and entrepreneurial courage have always been the foundation for the success of Rode and Schwarz. Making ideas real and striving for excellence. The spirit and mindset of our founders live on today and continue to evolve from one generation to the next. Every day, thousands of employees worldwide benefit from the knowledge that is accumulated in our company over decades. At Roda and Schwartz, they learn from each other, showing respect for that which came before them. We're part of this world and pass on our knowledge by providing the best possible solutions and systems. We've never made a secret of our innovation culture. At Roda and Schwartz, excellent development performance and entrepreneurial behavior go hand in hand. We make a difference. Driven by our distinctive passion for technology, we create the innovations that are highly relevant for a safer and connected world. Our customers and partners know they can always rely on us to deliver the highest quality. We are strongly positioned and look forward to a successful future. Our mission is clear: make ideas real. Yesterday, today, and tomorrow.
Making accurate antenna measurements in large chambers and outdoor antenna test ranges, or making long-distance measurements such as testing long cable runs on aircrafts or ships are not easy tasks. The traditional measurement solution uses a two-port benchtop vector network analyzer, a VNA, where the user must attach two very long test port cables. The problem with this solution is that long cables introduce signal loss, reducing dynamic range. To overcome this challenge, a high-end VNA is required, and components such as low-noise amplifiers are introduced to improve dynamic range. As the frequency of interest goes higher, however, small movements in the test port cables have an adverse effect on signal phase. Introducing the solution to long-distance S-parameter measurement problems, the Inritsu Shockline ME7869A. This modular two-port distributed VNA can make vector-corrected S-parameter measurements over distances as long as 100 meters. Complicated test setups and lossy cables are eliminated, since the instruments are powered by Inritsu's patented phase-link technology. This technology allows synchronization between the two VNA test ports using optical cables. No matter how much the user moves the cables, there's no phase deviation, while system dynamic range is fully preserved no matter the distance between test ports. Now you can confidently test long cable runs from aircraft's nose to tail and wingtip to wingtip, from ship's antennas to underdeck control rooms and antennas on outdoor test ranges, or in large anechoic chambers, all to full performance with a compact and easy-to-use solution. Inritsu, providing excellence in MM-wave measurements, covering the distance with our patented phase-link technology, integrated into the Shockline ME7869A modular vector network analyzer. Inritsu, advancing beyond.
Our product is called XDEC, which consists of hardware and software that we created in-house. We integrate our device with the semiconductor chip industry to help them reduce their cost for testing and get more reliable and also high yield of their product. The current problem in the semiconductor industry testing for the chip is because the current equipment is bulky, expensive, and also not integrated. Our solution provides technology that's 20 times smaller, 3 times cheaper, all integrated with easy-to-use software. Our device analyzing the reliability of the chip. This reduces the amount of defective chips and also puts out high yield in the manufacturing. It is important for the semiconductor chip manufacturers. So we have shipped our product to over 15 countries. Now also being used to different applications such as the AI, quantum, and also in data centers. NASA used for the space, US Army for defense, and the NVIDIA for the AI. For those companies, they use our equipment to be integrated with their systems to make it function properly in different applications. One of the best functions of our product is provide the voltage and current. Our equipment helps guide light so it can work properly into different applications. We are inspired to create more innovative devices so we can help people to have a better life around the world. This motivates our team every day.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with 2 main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs. Tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045 by consolidating science and technology resources and creating a resource ecosystem and research-based economical foundation. Transforming Indonesia as a global reference in the development and application of science and technology practices and the good of humankind. Nature is the source of inspiration. Knowledge is the foundation, and to be put in praxis for the sake of the nation.
Over 100 years ago, the discovery of radio waves marked the start of a new era. At that time, our founders Lothar Rode and Hermann Schwarz were still at school. They were immediately fascinated by this new technology and driven by a curiosity about the unprecedented possibilities it offered. Pioneering scientific spirit and entrepreneurial courage have always been the foundation for the success of Rode and Schwarz. Making ideas real and striving for excellence. The spirit and mindset of our founders live on today and continue to evolve from one generation to the next. Every day, thousands of employees worldwide benefit from the knowledge that is accumulated in our company over decades. At Rode and Schwarz, they learn from each other, showing respect for that which came before them. We're part of this world and pass on our knowledge by providing the best possible solutions and systems. We've never made a secret of our innovation culture. At Roda and Schwartz, excellent development performance and entrepreneurial behavior go hand in hand. We make a difference. Driven by our distinctive passion for technology, we create the innovations that are highly relevant for a safer and connected world. Our customers and partners know they can always rely on us to deliver the highest quality. We are strongly positioned and look forward to a successful future. Our mission is clear: make ideas real. Yesterday, today, and tomorrow.
Making accurate antenna measurements in large chambers and outdoor antenna test ranges, or making long-distance measurements such as testing long cable runs on aircrafts or ships are not easy tasks. The traditional measurement solution uses a two-port benchtop vector network analyzer, a VNA, where the user must attach two very long test port cables. The problem with this solution is that long cables introduce signal loss, reducing dynamic range. To overcome this challenge, a high-end VNA is required, and components such as low-noise amplifiers are introduced to improve dynamic range. As the frequency of interest goes higher, however, small movements in the test port cables have an adverse effect on signal phase. Introducing the solution to long-distance S-parameter measurement problems, the Inritsu
Recording in progress.
Miss Ardita, good afternoon, everyone. Welcome to parallel session 9 on electronic materials, component, and circuit. Let me introduce myself again. My name is Lia Yuliantini, and I'm from Research Center for Electronic BRIN, and I will be your moderator for this session. Thank you very much for coming today, and I have very happy to have you here. Today, we have 5 presenters joining us both on-site and remote in the Zoom meeting. Before we start the presentation, I will check the presenters' attendance first by calling their name and confirm their presence. For the first presenters is Mr. Wilman Septina from National Research and Innovation Agency. I see he has been here in the room. The second presenter is Miss Rosaila Matsna Muslimawati from Institute Teknologi Bandung. Are you there? Yeah, maybe she is still trying to connect with us. And third, Mr. Muhammad Raihan Zulfikar from Institute Teknologi Bandung. May I confirm your presence? Mr. Muhammad. Okay, thank you. Fourth, Mr. Iqbal Shamsu from National Research and Innovation Agency. Are you there? Mr. Iqbal Shamsu? Oh, okay. And five, Miss Danis Haraini from Universitas Negeri Yogyakarta.
Yes, I'm here.
Okay, thank you. And before moving into the presentation session, I would like to inform the short guidelines in this session. First, for all presenters have 9 to 11 minutes for presentation, and the remaining time is for Q&A and discussion session. Presenters who is in the Zoom meeting are kindly requested to keep their camera on during their session. And second, for participant, if you have any question, please feel free to raise your hand and turn your camera. You may also type your question in the chat box. And to keep on the schedule, let's start with our first presenter. Welcome, Mr. Wilman Septina.
Okay, thank you, Dr. Lia. Bismillah. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. My name is Wilman Septina, so I'm researcher at Research Center for Electronics. Today, I would like to present one of our research projects, so preliminary works on one of our research projects. So I will be talking about cesium-lead bromide solar cells for application as VV receivers in optical wireless power transfer, and I will compare the performance in air, and also in underwater. So this is the outline of my talk. So first I will start with some brief introduction about what is OWPT, and then some about the cesium lead bromide. Okay. Cesium lead bromide solar cells, and then goes into the materials characterization. Before I will show you the result of the tests of the photovoltaic performance in air and also in underwater. So first, let me start about what is actually OWPT systems and also the motivation behind this work. So to monitor the underwater conditions such as like this, so and also exploration, we need some reliable device network of devices. For example, for underwater vehicles, for sensor networks, and also for underwater communications. So as one of the potential solution is the system called optical wireless power transfer system. So what is this? This is basically delivering wireless energy underwater using some optical system. So in general, it is consisted of three main parts. So one is the light transmitter. It's coming from monochromatic light. So it can be LED or it can be also laser. In our case, it's laser, and also photovoltaic receiver. So and then the device itself, the load. So in this case, in this cartoon, is a sensor, for example. So that is the main components of all WPT systems. So in our case, we are interested in utilizing our WPT system using blue light. So why is blue light? Because if you see the cartoon here, this is the depth of the light penetration in water. So in x-axis, this is the wavelength of the light, UV, blue, green, red, and IR. And in y-axis, this is the depth underwater. So if you see here that the blue light in particular has deeper or the deepest light that can penetrate our water. This is with the assumption of clear water. So it has less attenuation compared to the other wavelength of light. And also, if you see the right graph here, this is the efficiency of the FIFI receiver in WPT system in general as a function of the band gap of the photovoltaic. And you see a correlation that if we increase the band gap, the efficiency of the receiver can be increased. This is according to these equations. So combining these two features, we can say that the choice of the FIFI receivers become very important to get the good efficiency. So then the FIFI using wide gap semiconductor, so with a high band gap, then it is suitable to harvest this blue light because this blue light is from low wavelength. So low wavelengths means high band gap. Okay, so in our case, we are interested to use cesium lead bromide due to several reasons. So this is ferroskyte type of materials. It has a wide band gap, so 2.3 electron volt. So that means it is suitable to harvest the blue light. And then it is by itself, it's stable in the presence of moisture. This is unlike a more conventional ferroskyte, the hybrid type, organic inorganic, which is usually unstable in the presence of moisture. But in this case, the cesium lead bromide is quite stable, relatively stable. And then also, which is very important, it can be fabricated without using a tools called glove box. So glove box usually needs inert environment such as nitrogen or argon to avoid the moisture. But in our case, we can fabricate this without the glove box. So in normal environment like this. So in the present works, we tested the screen printed cesium lead bromide solar cells as a potential application for blue laser driven OWPT. And then we tested the operation in air and also in underwater condition with encapsulated devices, which I will talk a bit later. So this is the experimental. There are many ways to fabricate cesium lead bromide solar cells, but in our case, we are using screen printed base method. So we fabricated a scaffold. We call it scaffold, which is a layered compact TiO2, mesoporous TiO2, mesoporous zirconia, and mesoporous carbon. Using screen printed, except the compact TiO2, we use spin coating. The others, we use screen printing. So this is, we call it scaffold. And then to fabricate the cesium lead bromide, we infiltrate. So we infiltrate, we put a solution of lead bromide in DMF, followed by immersion. So we immerse the sample in cesium bromide solution. And then later we did some annealing to get a device like this. So this is the device from top side, from carbon side, from top side, like this. So and then after we made this device, then we tested the performance under two different light sources. One is using AM 1.5, which is the standard light for solar cell measurement. It's a white light, as you can see here. The second, we use a blue laser with a wavelength of 405 nanometers. So it's a normal laser pointer like this, and this is our sample. So we tested the devices under two different conditions like this. So first, I will explain about the materials properties. So we tested first X-ray diffraction to know the phase of our fabricated film, and then we found out that the main phase of the material is cesium lead bromide, CSPB-BR3, but also we still found some remaining secondary phases, such as cesium Pb2, Br5, which is the cesium poor version of this phase, and then also lead bromide secondary phases. So we are still optimizing the process to get as pure as possible. But the main phase is already this. It is confirmed by the UV-Vis. So we measure the UV-Vis, the reflectance, and then by tau plot, we got the band gap, which is around 2.33 electron volt, which is the band gap of the cesium lead bromide. So that those are the material properties. So then we tested the full device. So this is the JV curve. J is current density, V is voltage. So current density, voltage. Under two different light sources. The black one is the white light. The red one is using the blue laser. And this is the parameter, the tabulated parameters. So the current density here, the VOC, the fill factor, and the power conversion efficiency. And yeah, one thing to note also that the power density of the AM 1.5 is a standard 100 milliwatt per centimeter square, but for laser, so we use as it is. So it has higher power, around 274.3 milliwatt per centimeter square. So it's quite intense. Then come back to the result. We found out that by using blue laser, we saw an improvement, a double improvement of the power conversion efficiency from 2.24 if we use the AM 1.5 to 5%. And so the improvement, if you see in more details here, is related to the improvement of the current density. So first is the current density, which is logical because we use a higher power of the light, and also more efficient absorption because now we are using only the blue light as opposed to the white light here. So we see a very significant increase of the current density. And also the second improvement was from the VOC, the open circuit voltage. So the voltage, we saw an improvement from 1.13 volt to 1.46 volt. So we thought this is due to the reduced process called recombination. So we don't want any of this recombination in the devices. but we thought that by using laser, more intense light, we reduce this kind of recombination. But the fill factor is dropped half because we thought that because it's too much current, but our electrode is maybe not conductive enough, so it is improvement for the future, room for improvement for the future. And then overall, we got 2 times improvement of the efficiency. Then we varied the condition of the measurement. So first, we vary the distance. So distance from the device to the light source from 10 centimeter and then all the way to 40 centimeter. And we didn't see any change, so it's relatively constant. It is a typical laser. So laser, the intensity is quite stable for a long distance, so it's also reflected in our cells, so it's quite stable. And also, we did some stability tests, so we continuously illuminated for several, it is only minute, so from until 4 minutes, so we did constant illumination to see whether our cells may be damaged or not. And we didn't see also any relatively the same, similar, except for the first minute, we saw a little bit some improvement, and then after that, it is relatively similar. So the device is stable with exposure to the high intensity of the laser. So then next, last, we tried to test them underwater. So because the solar cell itself, the perovskite, if we immerse without anything, without encapsulation, it will just dissociate. It will just destroy it. So we need to do some coverage. So in order to do that, we covered the solar cells with epoxy. So 2 types. First, we covered with a fast epoxy to get the fast drying, and then the slow dry epoxy to get more homogeneous coverage. And then we wire them like this. So then after that, we try to immerse the device inside the water like this. So for our preliminary testing, we use a normal beaker filled with normal tap water like this. So this is the device with the wire coming out from the beaker. And then this is the spot of the laser here. And then now this is the JV curves, air versus underwater. And for air, the black one here is air, red is the underwater one. And then it's also relatively similar. There is a little bit higher current in underwater. We still have to explore why, the exact reason, but probably because of more reflection of the light from the water, probably. But we still need to explore more about the exact reason for this. But our assumption at first is maybe more reflection of the light coming from the water itself. So, and also our device is not degraded. So even if we immerse the solar cell inside water, it still perform as good or similar as it is in air. So as a summary, so in this research, we tried to fabricate cesium lead bromide solar cell, and then we tested under 2 types of light, the M1.5 and also monochromatic laser. And we shows that the laser illumination has enhanced PCE, more improved efficiency and also quite stable performances. And when we encapsulated the device, so it has a robust performance underwater. So the performance is stable. And so our preliminary work shows that this type of perovskite solar cells is a promising candidate for this blue light PV receiver in underwater OWPT system. So we still need to improve the performance of the device, optimization of the process, and also optimization of the system. But this shows a quite good preliminary results. And this work is funded from Rumah Program, Jaringan Detektor Bawah Air Array BRIN. Okay, thank you for your attention.
Thank you very much for your interesting presentation, Mr. Wilman. If audience have a question, maybe you can raise your hands, or for audience in the Zoom meeting, you can use chat box feature. While we waiting the question from oh, okay, Mr. Widya, we have only 2 minutes, maybe only one question. Oh, yeah.
Okay, thank you. So my question is, did you try this GSPBBR3 underwater without any encapsulation? So it's how is sensitive with the humidity for this class of perovskite solar cell? Thank you.
Thank you. So, yeah, we tried. If if it is in air, it's relatively stable. Yes, stable. Even some at the beginning, it was improved the performance. If it is in air, if it is underwater without encapsulation, it's immediately gone. The cesium lead bromide. So it just dissociate into the component, the lead bromide and cesium bromide. We thought that way. So if without encapsulation, it's just destroyed. So it's just, it cannot work without encapsulation.
Okay, thank you very much for the question and for Mr. Widya. The question enough? And the answer enough? Okay, thank you. And maybe this is the end of Mr. Wilan presentation. Thank you very much. And you can back to your seat and enjoy the next presenters. Okay, and let's move. Let's move to the second presenter, Miss Roshaila Matsna Muslimawati.
Yeah, I'm here.
Oh, okay. Are you ready?
Yeah, okay.
Okay. Times is yours.
Hello everyone, my name is Roshaila Matsna Muslimawati. I'm from Institute Technology Bandung. Today I'm going to present our research about computational analysis of formamidinium tin iodide and cesium tin iodide perovskite solar cells using SCAPS 1D. For introductions, I'm gonna explain about lead-free perovskite solar cells. So recently, perovskite solar cells have attracted considerable interest, particularly from researchers and in the photovoltaic industry. Their efficiency increased from 3.8% in 2009 to 25%, which is attributed to their excellent optical and electronical properties and is on fabrication. The efficiency of this material have some advantage because they have characteristic of perovskite. First, high absorption coefficient and then large charge diffusion length, high hole mobility, and high electron mobility. Here I show about the device configuration or the structure of the perovskite solar cells. So there is standard and inverted structure, and for this one is for tandem perovskite solar cells as the reference for future application of solar cells. In this study, we focus on tin-based perovskites because of tin-based perovskite have a band gap around 1.2 until 1.4 electron volt, especially for tin-based perovskite. In this study, we focus on formamidinium tin iodide and cesium tin iodide as potentially absorber material for lead-free perovskite solar cells. So the main goal of this research is to understand how these materials perform and how their device efficiency can be improved through computational optimization using SCAPS 1D simulations. So in this work, we focus on inverted structure using P.PSS, S and HTL, and for the absorber, formamidinium tin iodide and cesium tin iodide, and for the ETL or electron transport layer is C60, and the electrode is silver. So in this figure, the proper band alignment between their valence and conduction band supports efficient charge extraction and reduce recombination losses, confirming the suitability for high-performance lead-free perovskite solar cells. The physical parameters for both perovskite material were adopted from previous reports, which are thickness, band gap, electron affinity, the electric permittivity, and so on. So this is we got from previous study, and we are gonna evaluate the thickness and then for the defect density and interface defect, also the temperature of the devices. So here is the initial parameter and the baseline performance of both formamidinium tin iodide and cesium tin iodide. So for the initial parameters, we got the thickness is 300 nanometer and defect density 10 to the power of 15 centimeter per cubic, and interfacial defect for HTL and absorber is 10 to the power of 10, and for the absorber and ETL is same, which is 10 to the power of 10 per centimeter cubic. So, we got from the initial parameter for the formamidinium tin iodide, the VOC is 0.95 volt and GSC 28 MA per centimeter square, and fill factor is 71.04%, and the PCE is 19%. And compared to the cesium tin iodide is lower VOC, which is 0.7, and for the PCE is 18%. So these simulations using the same initial parameters, and these initial results confirm that our simulation is aligned with previous reports, providing the reliable basis to the further optimization of absorber thickness, defect density, and interfacial properties in the next part of this study. In this part, we compare the effect of A-side cations, Fa plus and CS plus from this one, Fa plus and CS plus, on the performance of tin-based perovskite solar cells by varying absorber layer thickness. So we're varying 100 to 500 nanometer, and we got for the formamidinium tin iodide is stable for the VOC and for fill factor, but for the GSC is getting increased when the thickness is increases, and for the cesium tin iodide all of the performance is increased. So as we can see for the thickness 500 nanometers, we get the highest performance for the each material based perovskite solar cells. So for the formamidinium tin iodide, we got 19% for the PCE, and for the cesium tin iodide, we got 20%. So to further understand the role of defects in the device performance, we vary the bulk density from 10 to the power of 13 until 10 to the power of 17 centimeter per cubic. So for the thickness, we got from the optimized thickness, which is 500 nanometer. As we can see, for the formamidinium tin iodide, it's very unstable performance, which indicates strong sensitivity to trapped assisted recombination because for the defect, and for the cesium tin iodide also decrease, but it's not significant like for memidinium tin iodide. So for defect, for the possible defect of each material is contaminated with oxygen. So it is from experimental results from Lanzetta et al. So this diagram show the pathway highlight how intrinsic and extrinsic defects can strongly affect the stability and efficiency of tin-based perovskites. So in this part, we also looked the effect of interface quality, which is the interface defect on the device performance. So we got from the optimized thickness is 500 nanometer, and the optimized defect is 10 to the power of 13 per centimeter cubic. And for the interfacial, we got for the formamidinium tin iodide, it's lower for the interface of HTL and formamidinium tin iodide. So for the cesium tin iodide, we have more higher the interfacial defect tolerance. So it show that for the cesium tin iodide, we got more tolerance of interfacial defect than formamidinium tin iodide. So we also test the temperature dependence of both devices to examine their thermal stability. The results show that both formamidinium tin iodide and cesium tin iodide solar cells remain stable under temperature variation, indicating the device performance does not degrade significantly when the operating temperature increases. So finally, in this figure show overall performance comparison between the two devices, which is formamidinium tin iodide-based perovskite solar cells and cesium tin-based perovskite solar cells. We got two differences between this device. For the formamidinium tin iodide-based perovskite performs more constantly across different thicknesses and interfaces due to its larger Fa plus cation, which helps maintain lattice stability and carrier mobility. But in contrast, cesium tin iodide shows slight better defect tolerance and more stable interfaces. For conclusion, we got the initial performance for each devices, and after the optimization, for the formamidinium tin iodide maintains stable performance regardless of absorber thickness due to its larger Fa plus cation. And then for the cesium tin iodide depends on absorber thickness, as the smaller Cs plus cation induce lattice strain and shorter diffusion. But for the cesium tin iodide is more defect tolerant than formamidinium tin iodide. And for the formamidinium tin iodide, The interface between the ETL it's more stable than the HTL, but it's opposite for the cesium tin iodide show better HTL interface stability. Both stable under temperature variation, and after the optimization, we got for the formamidinium tin iodide, we got efficiency 26%, and then for cesium tin iodide, 24%. Thank you for your attention.
Sorry, Miss Leah, I can't hear you. I think it's still muted.
Okay. Thank you for presentation. Can you hear me?
Yeah, very clear.
Okay. Okay. Thank you for sharing your present work. And in your current work, you use PIN structure, right? Okay. And can you explain the reason why you use PIN structure for combining the PSG and tandem with silicon solar cell? Can you give some reason for your work?
Oh, okay. Thank you for the question, Miss Leah. For the reasoning, I choose the PIN structure because for tin-based perovskite, it's for the NIP structure. I mean, for the standard structure, it's not that stable. It's not that stable because there is some issues for tin-based perovskite with oxygen. So when we applied to PIN structure, we can choose the material without the oxide base. Yeah, normally for the NIP structure, you using oxide base for the structure, but for the PIN, it's without oxide base structure. So additionally, for the tandem silicon perovskite solar cell is in my best knowledge, the structure also PIN. So that's why I want to know for the PIN structure if the absorber using FA SNI3 and CS SNI3.
Okay, one question for me. And you use ETL in your PSG is C60 for ETL.
Yeah.
Yeah. Can you give me another material? Maybe material that can we use for the structure and suitable for FA SNY-I3.
Yeah, of course, for the ETL, we can use another material like polymer based like PCBM or maybe the other material like mm, yeah, I think PCBM it's most used for the ETL, PCBM or C60 for the FA SNI3 base solar cells.
Detailed explanation. Maybe is there any question from audience?
Thank you, Ms. Rosaila. So, how you did the temperature variation in your simulation? What parameter did you change to to see the temperature stability of your materials?
Okay, thank you for the question, Mr. Wilman. So after I got the optimized structure from the SCAPS 1D, in that software, we can find the parameter of device like temperature or voltage and the how can I say, the resistance. It show in SCAPS 1D. So after we optimize layer by layer, we can change the temperature in the main view of the software. Is it good? Is it enough for the answer?
I think Mr. Wilman have satisfied answer from Ms. Rosaila. Because of the limitation of time, thank you very much for Ms. Rosaila. Please give applause.
Thank you very much.
Yeah, thank you, and you can continue enjoy the next presentation. And let's move to the third presentation. Mr. Muhammad Raihan Zulfikar, are you ready?
Hello everyone, my name is Muhammad Raihan Zulfikar from Institute Technology.
Yes, I'm ready. Sorry.
Geographical location near the equator, allowing sunlight to be received over the years. According to the National Energy Council, Indonesia has solar potential reaches 4.8 kilowatt-hour per square meter per day, which is equivalent to more than 112,000 gigawatts peak when considering the total land area. Solar energy as a renewable and environmentally friendly resource represents one of the most promising solutions for sustainable electricity generation. Its enormous potential provides a strong motivation to advance solar cell technologies as part of the global renewable energy strategy. Solar cells are efficient devices that directly convert sunlight into electrical energy through the photovoltaic effect. Over the years, several generations of solar cells have been developed, from crystalline silicon-based to thin film and third generation devices such as organic and perovskite solar cell. Among these, perovskite solar cells have gained significant attention due to their high power conversion efficiency, low cost production, and simple fabrication. Typical perovskite solar cell consists of 5 layers: the transparent conductive oxide or glass substrate, the electron transfer layer, the perovskite layer, the hole transfer layer, and electrode. However, recent developments have shown that it's possible to eliminate the hole transfer layer, resulting in what we call hole transfer layer free perovskite solar cell. This architecture reduces fabrication complexity and cost, while improving device durability by removing unstable organic hole transfer layer free material. In this configuration, carbon-based electrode serve as both the hole transfer material and the counter electrode, replacing expensive noble metal like gold or silver. Carbon has work function of around 5.0 electron volt, closely matched that of gold, around 5.1 electron volt, facilitating efficient hole extraction at the perfect carbon interface. Carbon materials such as carbon nanotube, carbon fiber, carbon black, graphite, and graphene has been widely explored for use as electrode due to their excellent electrical conductivity, chemical stability, and tunable surface morphology. However, there are still key challenges associated with commercial carbon-based. First, the low interfacial contact between the carbon electrode and the perovskite layer often results from poor interaction between the beta and the carbon particle, reducing charge transport and overall device efficiency. Second, the high cost of commercial parts increasing overall fabrication cost. The binder plays a The binder play a crucial role in carbon-based formulation as it ensures strong adhesion of carbon particle to the substrate, maintain the mechanical integrity of the electrode layer, and promote better particle dispersion, film uniformity, and interfacial conductivity. Therefore, optimizing the binder material is essential to improve interfacial contact, enhance mechanical stability, and achieve cost-effective carbon-based electrode. Conventional binders such as styrene butadiene styrene (SPS), polymethyl methacrylate (PMMA), ethyl cellulose, and toluene have been explored. This highlights the need for alternative binder material. One promising candidate is polyphenylidene fluoride, or PPDF, a semi-crystalline thermoplastic fluoropolymer known for its excellent mechanical strength, chemical resistance, and electrochemical stability. This property have made it a dominant binder in lithium battery electrode for decades. In this study, we aim to formulate a graphite carbon black paste using PVDF as binder, which is then deposited on FTO substrate. The prepared paste is characterized in terms of its structural, interfacial, and electrical properties. The main goal is to assess its potential for use as a stable and low-cost electrode material in whole transport layer-free perovskite solar cell. In this study, we use graphite, carbon black, PVDF binder, dimethyl formate as solvent, and FTO glass as the conductive substrates. To prepare the PVDF binder solution, PVDF powder was dissolved in dimethyl formate at 10% concentration. Further mixing, the carbon black was thermally treated using a blow thrust for 30 minutes. Next, the treated carbon black was combined with graphite powder in a 3:1 weight ratio, forming the main conductive matrix. This carbon mixture was then blended with the PVDF binder solution, also at 10% concentration, and stirred strongly until a homogeneous paste was obtained. The resulting graphite carbon black PVDF paste was then screen print on FTO substrate and annealed at 100 degrees Celsius for 10 minutes to ensure solvent evaporation and proper adhesion. For comparison, a commercial carbon paste from Tecotec Material Ltd was also characterized using Raman spectroscopy. The prepared sample was characterized to evaluate their structural and electrical properties. Raman spectroscopy was used to study the effect, structure, and crystallinity of the carbon film, employing a thermoscientific TXR3 spectrometer with 5 mW laser power. Electrochemical impedance spectroscopy ACE was carried out using a Cortef JS350 system to determine charge transfer resistance in valence and KCl electrolyte across a frequency range of 0.1 Hz to 10 kHz. Electrical conductivity measurement was performed using a 4-point probe set up with 2 mm probe spacing, while the current voltage IV measurement were obtained using a Catley 2400 source meter, scanning voltage between -1.5 and +1.5 volt to investigate interfacial transport behavior between the carbon layer and FTO substrate. The Raman spectroscopy results shown here on the left, with the corresponding data double on the right. As shown in the figure, both graphite carbon black PVDF and commercial Tecotec carbon paste display the three characteristic Raman peaks located around 1,355, 1,580, and 2,670 centimeters, corresponding to the D, G, and 2D bands, respectively. Intensity ratio between the D and G band, ID, IG, is common indicator of defect density. A lower intensity D intensity G ratio suggests fewer structural defect and a higher level of gravitation. In the study, the graphite carbon black PVDF sample exhibit an the intensity D and G band ratio of 0.92 compared to 0.98 for the Tecotec paste. This indicates that the standard carbon electrode possesses better crystallinity and fewer lattice imperfections compared to previous literature. For instance, Wang Xi et al. Report an ID ratio of around 0.99 for carbon black graphite composite. Our material exhibit lower defect density, which is favorable for Chinese transport, a more ordered carbon structure, and has carrier mobility and reduced scattering, leading to better overall electrical performance. Additionally, the presence of broad 2D band near 2060 670 cm further confirm the multi-layer graphitic structure with the electrode. The shape and position of this band are consistent with tachygraphian layer, suggesting the formation of extended graphitic domain. So here with the next is AIS analysis. So here with the NQS plot and the equivalency graph on the left and the fitted data table on the right. Electrochemical event-based spectroscopy was conducted to study the charge transfer behavior and recognition dynamic and the electrode substrate interface. As in the figure, the spectra were well fit by an equivalent circuit model consisting of series resistance RS and parallel RCPA network representing the charge transfer resistance RCT and interfacial capacitance respectively. At lower frequency, a short wave element appears, indicating the presence of diffusion and mass transfer effect which are common in porous carbon structure. For the graphite carbon black PVDV electrode, the fit RCT value is approximately 164.4 ohm as summarized in table. This relative low RCT suggests efficient charge transfer across the electrode interface and good electronic connectivity, both of which are important for solar cell operation. These findings are comparable to other carbon-based composites. For example, Lee et al. Reported the LGO GMK5 electrode exhibit similar low frequency warp behavior due to enhanced ion diffusion through interconnect mesoporous channel. Moving on the IV and for power result, the IV curve shown on the left indicate distinct interfacial behavior between the electrodes. The BRFU substrate display ohmic response, while the actual graphite carbon black PVDV electrode exhibit non-ohmic or rectifying behavior. This non-literally suggests the formation of an interfacial barrier or Schottky type junction, which is desirable for photovoltaic application. Such interface can facilitate unidirectional charge transport, minimize recombination loss, and enhance photogenesis current extraction in perovskite solar cell. The interfacial behavior is strongly influenced not only by the mechanical addition of the phase, but also by energy level alignment and chemical compatibility between the carbon layer and the substrate. Weak van der Waals interaction, for instance, can hinder charge transport. So, observation by chemistry such as using PVDF is crucial to achieve both good addition and favorable energy alignment. On the right, the 4-point probe result show that the resistivity of the graphite carbon black PVDV film is 0.005 to 5 ohm centimeter, corresponding to electrical conductivity of 190.6 Siemens per centimeter. This value is significantly lower than those report for other binary systems such as PMMA, SBS, AC, and PVSC, which typically exhibit resistivity in the range of 0.5 to 0.8 ohm centimeter. The high conductivity achieved here is attributed to the optimal graphite to carbon black ratio 3:1 and the strong binding capability of binding PVDF as binder, which is ensure uniform particle distribution and continuous conductive bed switch. Last slide, conclusion. The graphite carbon black PVDV electrode fabricated on FTO substrate exhibit with a combination of excellent material structure and favorable electrical performance. Raman spectroscopy revealed a low dBn ratio of 0.92, indicating enhanced graphitic and ordering and reduced defect density. AIS measurement confirmed efficient charge transfer with an RCT value of around 164 ohm. The IV analysis saw a non-ohmic contact consistent with the desirable interfacial characteristic for photovoltaic device, and the 4-point probe test yield a high conductivity of 190.6 Siemens per centimeter. Overall, this result demonstrates the incorporation of PVDV as binder not only improve film formation and addition, but also enhance the electrical connectivity with the carbon matrix. Thank you for your attention. I will be glad to take any questions.
Any question from audience in this room or maybe in the Zoom meeting?
Okay. Thank you for your nice presentation, Mr. Muhammad. So I have a question. So you mentioned about the procedure. In the procedure, correct me if I'm wrong. So you mentioned about PVDF, carbon black, and solvent, right? So correct me if I'm wrong.
Yes.
So I want to know what is the solvent you used for PVDF?
I use the middle format for solvent.
Okay. And also, you mentioned about several binder in previous study, right? So yeah, you compare about you show the data about the comparison data about the resistivity. And I want to know that you also have you compared or do you have any comparison data about IV?
No, I don't have any data for that binder, those binder.
Also, you only have the data comparison data about the resistivity.
Yes, only from the literature.
Okay, thank you. Thank you.
Question from Ms. Nunik and any other question? No, maybe one question from me. Can you explain why you use that binder and that solvent in your present work?
Okay, thank you. The next question. The PVDV was chosen because of its excellent mechanical strength, chemical stability, and strong adhesion properties. And these properties make it particularly stable for forming stable carbonic word, which is beneficial for waveguide solar cell application.
Hello? And for the solvent, why?
Oh, well, I use the solvent because the literature told the best solvent is PVD for PVDV as the metal format. I only follow the literature first.
Okay, okay. Thank you very much for your answer and presentation, Ms. Muhammad. We have reached the time and give applause for Mr. Muhammad Raihan.
Thank you so much.
Okay, and let's continue. Before we continue to the next presenters, we have screen capture for participant who join in the Zoom meeting. Please kindly turn on your camera. Our host and co-host will screen capture. We have only one page here. I will count. 1, 2, 3. Okay, thank you. And let's continue to the fourth presenter, Mr. Iqbal Shamsu from National Research and Innovation Agency. Screen is yours.
Thank you for having me to present at this conference. It is an honor to be here today for presenting our work on novel fluorine sensor. And this research addressed to fundamental public concerns, as free chlorine is the most vital disinfectant used in water treatment. So in nature, where the water cycles enforce continuous circulation, we face a fundamental challenge in maintaining optimal chlorine levels. If we use too little, we risk microbial growth and compromising public health. But too much can create harmful chlorination byproduct and cause irritation.
Reliable and real-time monitors are needed that can operate online to keep this level as expected. Free chlorine is the effective sanitizer that present in water, while high combined chlorine levels are an indication that the active chlorine has been used up and the water needs treatment. So currently, the gold standard method like colorimetry and titration or laboratory analysis are effective, but are also time-consuming, rely on manual sampling, and simply cannot provide continuous for online measurement. The semi-resistive sensor platform was chosen because it features it offers the key advantages of fast response, low cost, and portability, and it's ideal for field use devices. The core challenge then becomes the sensing material itself. The sensing material is a composite of graphene oxide and the conductive polymer PEDOT-PSS, or simply PEDOT. The graphene oxide was synthesized using a modified hammer methods to maximize the oxygen functional groups on its surface. These groups are the active sites where the chemical reaction with the chlorine happens. When graphene oxide is combined with PDOT, a highly conductive and stable polymer, a synergistic effect is achieved. The object was to create a scalable fabrication process, and here alumina substrate was used for its durability. The electrodes were created using thick film screen printing. This is a low-cost and mature technique that's been proven for mass production. Silver paste was screen printed in an interdigitated form. Then the electrodes were baked at a high temperature of 800 degrees Celsius for about 15 minutes. This ensures a robust adhesion to alumina and excellent conductivity. There are two separate dispersions were prepared. First, a diluted and stirred PDOT, and dispersed and ultrasonicated graphene oxide. They were mixed in a 1:4 ratio and sonicated and stirred to form a homogeneous composite. For deposition, a drop casting method was used to the interdigited electrodes. Three samples were fabricated with increasing numbers of drops and layers, resulting in thickness from about 70 to 150 nanometers. Each layer was dried and thermally nailed in stages. With a final cure at 120 degrees Celsius to strengthen the film. This control process ensures a uniform distribution of graphene oxide within the polymer and allow the film thickness to be tuned for performance optimization. XRD was used to confirm successful graphene oxide synthesis. The graphite powder showed a sharp peak about 26 degrees corresponding to the 002 plane. After oxidation, the peak disappeared and the new peak saw at about 10 degrees. This shift confirms the increasing of oxygen group and water molecules between the layer. Then FTIR analyze so key functional groups. It validate the presence of hydroxyl, carboxyl, and alkoxy groups. It's a clear evidence of a successful graphite oxidation. Together, the result confirmed that the graphene oxide is exfoliated and chemically functionalized. making it suitable for integration into the sensing platform. Let's see the characterization of the screen print silver electrodes, which serve as the foundation of our sensing layer. Using a stylus profilometer, the silver film thickness was measured to be approximately 4 microns with some variation across the surface. This confirmed that a stable and conductive layer was successfully deposited. Surface roughness was another key parameter. The silver electrode saw a similar average roughness with the alumina substrate. This close match in topography is highly beneficial. It ensures uniform deposition of the sensing layer and increasing mechanical bonding. Using SEM imaging, a well-formed continuous film with a rough surface was observed. The graphene oxide sheets were uniformly embedded within the P dot matrix, confirming a homogeneous dispersion. While minor agglomeration appeared in some larger zones, the overall distribution was consistent. EDX analysis was performed to verify the material composition. The spectrum saw carbon, oxygen, and sulfur as the dominant elements. The presence of sulfur and carbon confirmed the P dot polymer, while the oxygen and carbon contents validates the presence of graphene oxide. A strong silver peak was detected corresponding to the underlying electron. Let's through the sensing mechanism behind our graphene oxide P dot composite sensor for the free chlorine detection. The key player here is the hypochlorite ion. It's an oxidizing agent present in chlorine solution. When the sensor is exposed to this analyte, two simultaneous reactions occur. First, hypochlorite alters the carbon lattice of graphene oxide, reducing its conductive pathways. Second, it oxides the P dot polymer, triggering a dedoping effect that strips away charge carrier that essential for conduction. The result is a significant drop in the overall conductivity of composite film. This redox-driven loss is what measured as a negative current response. The reaction itself is concentration dependent. Higher chlorine levels mean more hypochlorite ions. This synergistic behavior between two materials is what enables the sensor high sensitivity. Samples were tested with 1, 2, and 3 composite layers, each exposed to a standard 10 milligram per liter chlorine solution. As the number of layers increase, the magnitude of the current response also extends. This enhancement is related to the greater amount of active sensing material available in thicker film. Why does it matter? A thicker layer provides more reaction sites for the chlorine to interact with, which amplifies the redox-driven charge transfer process. This leads to a more significant shift in hole concentration, causing larger change in the measurement current. The sensor was monitored over a 360-second period across various chlorine concentration, and the current dropped sharply within the first 15 seconds of exposure, indicating a fast interaction with the analyte. Following this response, and the current gradually stabilized. It shows significant chemical equilibrium between descending composite and free chlorine. This line current show a clear linear relationship with chlorine concentration. From this, the sensor sensitivity was calculated to be approximately 0.2 microamps per milligram per liter. Additionally, the response curves for different concentration are well separated, which confirm excellent signal resolution over time. In summary, we have successfully developed a rapid, sensitive, and reproducible semi-resistive free chlorine sensor using graphene oxide PDOT composite. And this work proves that combining this material with scalable thick film screen printing offers attractive, economically sensor manufacturing. Finally, the sensor delivered competitive metrics. The sensitivity of approximately 0.2 microampere per milligram per liter is a relative fast response time under 15 seconds. And by integrating this material with scalable thick film screen printing, it has economical potential for sensor manufacturing. Looking ahead, the next work will be optimizing the graphene oxide PDOT ratio and studies on long-term stability and selectivity. Also, to achieve miniaturization for portable and real-time pre-chlorine monitor. Thank you for your attention. I'm happy to take any question you may have, all of your comments, and also society.
Okay, thank you very much for your nice presentation, Mr. Iqbal. Any question here from audience?
Thank you, Pak Iqbal, for the presentation. I have a question. My first question is, can you tell us the reason for choosing graphene oxide in this work instead of graphene? And for instance, if we replace graphene oxide with graphene, can we expect a better result or anything, or maybe even worse result? And then my second question is, what solvent did you use to redisperse for the graphene oxide? For graphene oxide dispersion, did you use water or any other solvent? Thank you.
Okay, thank you for the question. First, why we use graphene oxide instead of, for example, just pristine graphite. So the graphene oxide is selected over graphite primarily because of its high surface area and the presence of the abundant oxygen functional groups such as hydroxyl and so on. And then, unlike the chemically inert and hydrophobic graphite, these functional groups make graphene oxide highly hydrophilic, allowing it to be readily exfoliated into single sheets and stably dispersed in aqueous solution, which is essential for creating uniform composite layer with water-soluble polymer like PDOT through solution-based processing. Furthermore, this group act as active site for chemical recognition and provide excellent points for the polymer. It's leading to optimize charge transfer and dramatically higher effective surface area for sensing. And they'll be posting the sensor sensitivity and and also lowering the its limit of detection. And the second question, if I'm not wrong, it's about the solution. Yeah. I use simply DI water to soluble the P dot. Only use the DI water. Thank you.
Okay, I think the answer is enough. Thank you, Mr. Iqbal. I think we have any question here, but we are really sorry we have limited time. And let's give applause for Mr. Iqbal Samsul.
Thank you.
Let's continue to our last presenter, Miss Denis Haraini from Universitas Negeri Yogyakarta. Times is yours.
Good morning, everyone. This is Dennis Hardy. I'm honored to present our research at the International Conference in Radar, Antenna, Microwave, and Telecommunication Technology of 25. Today, I will discuss the transport layer of all inorganic perovskite solar cells. Perovskite solar cells have emerged as a highly promising third-generation photovoltaic technology owing to their long carrier diffusion length, tunable band gap, and higher absorption coefficient. Perovskite have a general ABX3 structure where A is a cation, B is a typical of metal such as lead, and X is a halide ion. In all inorganic perovskites like GSPBr3 has a GS, PB, and Br ions forming a robust three-dimensional lattice, making it highly suitable for efficient and stable for solar cell. All inorganic perovskite, such as GSPBr3, offer remarkable advantage over their hybrid counterparts, which this improved structure. GSPBr3 enable higher carrier mobility, supporting faster and more efficient charge transport with the solar cell, as shown on the radar diagram. To right, GSPBr3 also exhibits a higher band gap and a longer diffusion length compared to other composition, contributing to its superior operational profile. However, there is a catch. Despite tree strength, all inorganic perovskites still lag behind hybrid system in the terms of device efficiency. The main reason is that while stability is maximized, certain interface and transport layer bottlenecks limit the harvesting of their full optoelectric potential. Because of this, the real breakthrough on the performance will occur not just by choosing GSPBr3, but by simultaneously engineering the device interface, especially the carrier transport layer. And if we can optimize this layer to match GSPBr3 unique physical properties, so we can close to the efficiency gap and realize the full promise of all inorganic perovskite solar cell. The electron transport layer on the GSPBr3 is central to the function of perovskite solar cell. Its main job is to enable smooth electron flow, block hole, and suppress the recombination at a critical interface. If the ETL works well, every electron generated by light in the active layer has a clear pathway to be collected. For instance, the resets, so that when we use the ionized water, we get a relatively high performing and environmentally friendly ETL. Switching to the ethanol makes film more homogeneous and sometimes which improve efficiency. And with isopropanol, as we can see in our study, is outstanding for crystal growth, transparency, and device performance. Device disadvantage limitations first. Pairs comparison when different systems are not always fair because their perovskite layer themselves can vary. So the synthesis routes for SNO2 have not been universally simplified, and we still lack comprehensive studies on how specific solvent choice to shape the final ETL properties. That's why SNO2 continues to stand out as a superior candidate because it's over a wide energy band gap with high electron mobility and a good optical transparency. To overcome this limitation, we introduced a simpler and identical SNO2 preparation protocol using 3 different solvents. First, the ionized water, ethanol, and isopropanol for film fabrication. And we focus how solvent properties such as boiling point, surface tension, viscosity affect film and device performance. Through careful solvent engineering, we can supercharge recombination, enhance fill vector, and PCA, and ultimately create highly uniform defect-free SNO2 layers that boost the performance of various solar cells. We employ the salt gel method for the SNO2 layer preparation with each solvent. The protocol we applied, the first is for dionysus water, SnCl2 to H2O and urea were mixed and stirred at room temperature for 48 hours. And for ethanol and isopropanol, SnCl2 to H2O was dissolved and stirred at 400 rpm with varying underlying temperatures and time according to the solvent. Yes. So the SNO2 precursor solution was the deposits on the FTO substrate and followed by GSBB battery perovskite film formation until carbonized. All samples show a sharp absorption age around 530 nanometer, which match what we expect from the GSBB band gap. And interestingly, the SNO2 film produced using the ionized water appears to have highest absorbance across the visible spectrum. At first glance, it might suggest better light harvesting. And however, a closer look reveals that this higher absorbance is actually due to increased scattering, often a sign that the film is uneven or contains more defect. As we move longer wavelength, the absorbance curve flattens out. This pattern points subtle change in light interaction possible due to electronic defects on the ETL. When comparing the different solvent of SNO and ethanol layers stand out for having a broader absorbance tail. This indicates the higher density of trap states, which result from rapid solvent evaporation and less uniform film formation. So why does this matter? The effect, especially traps, can hinder charge transport efficiency and negatively affect both the PCA and lifetime the solar cell. And to confirm that these different are rooted in the ETL and not in the perovskite, we turn into the touch plot here. So all samples show a sharp increase electron excitation around 2.3 and until 2.35 electron volt, consistent with GSBB battery, no one band gap. This assures us that the main factor driving this difference in performance is not a change in intrinsic perovskite properties, but rather than interface quality determined by choosing ETL solvent. In this graph, the device using SNO2 prepared with isopropanol stand out by achieving the highest values for PCA, GST, and fill vector. This performance is not coincidentally is a causally linked to the superior quality of the ATL layer produced with IPA. A high fill vector means that the device has very low series resistance and excellent hole blocking capability, greatly suppressing recombination losses at the interface. This is directly visible in the power voltage plot the IPA base cell maintain a stable and high working voltage even under load and deliver maximum power output that is well above the other sample. And the other hand, the device using SNO2 from the ionized water suffer dramatic drop current at this low GHG indicates that many carrier uh, are being lost, like due to leakage caused by shunting or pinholes in the ETL resulting from poor film uniformity. And meanwhile, the eternal base device display a lower open circuit voltage, pointing to the higher charge state density and less perfect electrical contact. In this case, more charge carriers recommend 9 before they can be collected, which lower both current and overall device efficiency. The curve for the SNO2 EPA-based device tell a compelling story. The device displayed the lowest leakage current, especially near 0 volt, and the curves is sharp and wide, signaling a strong diode behavior. Why does this matter? Because low leakage current and a pronounced curve area mean that the ETL is doing its job successfully, blocking holes and ensuring that electrons flow efficiently with minimal undesired recombination. So the physical structure is free from major defect like pinholes, so current can bypass the intended pathway. By comparison, device with the SNO2 prepared in ionized water or ethanol show higher leakage current here. That reveals that their ETL are less effective, likely due to microscopic defect, the imperfection that let current slip through the wrong way. So this flavor not only reduce the diode ability to block holes, but also open up roads for non-radiative recombination, ultimately robbing the device of power and stability. Yeah, so this is the conclusion about this research. This study demonstrates that the SNO2 electron transport layer significantly impact performance of GS3 perovskite solar cell, and EPA was proven highest power conversions and efficiency, lowest leakage current, and optimal GP parameter. But the ethanol and diodes motor increased charge recombination, decreased device performance. So this finding confirmed that the selection of the appropriate solvent is the fundamentally strategy for maximizing the efficiency. Thank you for your attention.
Thank you very much for your good presentation, Miss Denise. Any question here from audience? If there are no question, maybe while we waiting the question from audience, I have one question. So in the present work, you use 3 solvent, DI water, ethanol, and IPA, right?
Yes, right.
Yeah. And you in the PST fabrication, you did not use heating for DIY and ethanol ETL.
Excuse me, can you repeat the question?
You didn't use heating process in the fabrication, the position of the ETL that use DI water and ethanol.
Did you mean preheating or
Yes,
anode?
yes, preheating.
For preheating, I use preheating for the SNO with ionized water for solution, but for the ethanol SNO and isopropanol, I have no do preheating.
So, what the reason you choose different fabrication in that ETL? Can you give me the explanation about that?
Okay. As we know that the ethanol, isopropanol, and ionized water have a 3 psychochemical. First is a boiling point. We know that isopropanol have a high, low or medium boiling point that it can more make spread faster and then make the form of crystal nicer, and then the viscosity of isopropanol is higher than other, so the solution can spread lower, and then with the higher density surface tension, we can the solution can spread more lower and then smooth, so it can be more good for the crystallinities. But in the ethanol and the Dionysus water, we know that the boiling point is different from the isopropanol. So this is why I use a preheating for just to the Dionysus water, but not to isopropanol and ethanol, like that. Okay. No.
Okay, thank you for your answer. Or any question here? Maybe one question from me. You have a different value of VOC in your GV curve.
I'm sorry?
Yeah.
Different?
Can you give me? Yeah, you have a low value of VOC for IPA, and what your next plan to improve the VOC?
Okay. So far, I just think that to improve the VOC with the isopropanol in SNO2, I have to maybe try to varying the to preparation of isopropanol SNO2, because until now I just try to prepare the SNO of isopropanol with one variation of jadi I have to try more variation for preparing the solvent of SNO2 isopropanol, maybe with the different misalnya dengan suhu yang berbeda gitu saat difabrikasikan seperti itu.
Okay, thank you very much for your nice answer, Miss Denise. And Miss Denise is our last presenter here. Let's give applause for her. And this is the end of session. Maybe I will try to conclude our session that our discussion highlight the development of various devices such as perovskite solar cell and sensors, along with new composition for carbon beside electrode. This innovation not only show the significant scientific progress, but also show continuously improving the performance of our device. And also, this is the end of my session, and I will return the floor for Master of Ceremony.
Thank you, Dr. Lia Yuliantini, for having moderated the Pearl session 9. We regret to inform attendees that the keynote talk by Professor Dr. Katia Galuh has been cancelled due to the speaker's health condition. We appreciate your understanding and we wish her a swift recovery. And now we have come to our train patron award. Will be delivered by Dr. Andre Mahendra from Next Lab, and the session will be moderated by Professor Dr. Natalita Maulani Nursam. I will read her short profile. So, Professor Dr. Natalita Maulani Nursam Center for Electronics from National Research and Innovation Agency of BRIN Indonesia, and she completed her PhD in chemistry from University of Melbourne in 2016. She joined Indonesian Institute of Sciences, OLIPI, in 2011
Recording in progress.
and was promoted to research professor in Indonesia's National Research and Innovation Agency of BRIN for the research group of advanced photovoltaic and functional electronic devices. Her expertise area are solar cell and semiconductor devices. Please welcome Dr. Andi Mahendra and Prof. Dr. Natalita Maulana.
the ATE, automatic test equipment, for chip verification. For example, you have a chip after tape out in the semiconductor foundry, you want to test the SPI or microprocessor inside memory. So we also create the device for our client in worldwide. And we also provide the software on top of the hardware. So the software itself is a graphical user interface, but we also provide many templates for users like researchers, scientists, or engineers if they want to have Python's compatible C, C Sharp, LFU, and many, many more. And recently we also have the chip. This is our own chip design, basically the integrated photonics and electronics. So we design also photonic chip. We provide a service. So if researchers from audience interests collaborating with us to design, we work with the foundry in the US, in Europe also to tap out. We can help with running or submission for MPW also, multi-project wafer. So how our product works, basically our device just only need single source of power supply, DC input to the device, and then you actually can scale the outputs. We provide several different device, basically 8 channel, up to 1,000 channel you can actually combine together in the single software. And recently we deploy this more than 2,000 channel in one single foundry in Europe. So this is one of also validation of the equipment itself in the advanced semiconductor industry. So basically you can control these equipment with workstation, your PC or laptop, and then you can test your device with a different configuration. If you use need a RF source or combine other instruments with optical signal analyzer or anything, you can also combine with our equipment and doing some triggering on that functions. So our vision is actually not only supporting in the photonic integrated circuit industry, but also we also create different verticals here, not only the automation on the semiconductor advanced equipment, but also we provide driver for the quantum photonics, integrated beamforming, the next 5G beyond. And we also supply to many industry in different areas such as AI or next generation chip. So we already shipped to over 20 countries so far, and mostly in Japan, US, and also in Europe. And this is mostly our customers. So not only in instrumentation side, but applications such as in quantum and AI, we have many users that also collaborate with us, especially in the university or industry that they co-develop our product with their requirement. And we also apply to telecommunication and also data centers to help them a more advanced equipment. So this is our team. We have currently have a team in Bandung mostly, and we have a team in the US. And we backed by many investors in the US, including a New York State government. So we part of Luminate program in Rochester, New York. And we covering our product with intellectual properties. We have 2 US patent granted and several patents also ongoing for the mixed signal architecture and chip design for the future device. And this is also our collaboration between the global community, where we also working or connect with many customers around the world. We have exhibition not only in Asia, but also in the US and also in Europe. And several use cases, which probably can relate to all the audience here. We have several users, for example, this one from ICE and also University of Tokyo, where they use our product to control their chip, the photonic integrated circuit chip, to do the AI accelerator device. And then this is also one of the milestone that we see a lot of other researcher or customers around the globe use the same device to do the same things. And the second one is from NASA and GPL. We ship to NASA to help them actually control the integrated spectrograph, to help them explore or find a new planets outside our universe. And this is one of the other implementation where our device can be used for wafer level testing, where they can test a laser-based testing or a chip scale after wire bonding or just before wire bonding, so you can verify doing in-burn testing or functional testing. Another use case is in the telecommunication industry. We have customers that doing research with their chip to actually increase the bandwidth of the telecommunication infrastructure. And this is also one of our customers in Japan and also in India. They developed the next 5G tower using photonics integrated circuits. Another application related to the computing, basically, this is one of the arithmetic photonics processor that being developed by team in China. They use our product to help them control the configuration of the system. And the last one probably related to the automotive industry, where we also co-develop with them. Currently, we work with this TUI, Technical University of Eindhoven, together with the development of new device that they require to use the LiDAR photonic chip for higher range and a higher power collaboration. So the next call, probably we would like to probably invite all the audience or participants, because our role as an industry, we want to bridge the gap between your research and also to the commercialization of the device that you develop. And we hope that we can drive more technological collaboration, not only in Indonesia, but also around the globe, so we can have more efficient data, but also efficient device for semiconductor advancement in the future. And another of message, probably we also try to build a talent around our company, and hopefully we can bridge between this research and industry ecosystem. Thank you.
Yeah, thank you very much, Pak Andri. We still have more time if you still have something to deliver to the
Probably,
audience.
yeah, welcome any questions.
Okay.
Yeah.
So I'll go directly to question and answer. We have first question from Priyo.
Assalamualaikum warahmatullahi wabarakatuh. My name is Priyo. I'm from a research center for telecommunication. My passion work is in RF device. I already talked with some of your colleagues or your teams about the really me personally is very interested about the SMU, short measurement unit, and then maybe only a suggestion once about the graphical user interface. I think you should put the, let's just say, the IV curve more like just the graphic, not just put it in CSV, something like that. And then the second one, I would like to know about the, let's just say we do the parameter sweeps. How is the minimum, the minimum, let's just say we put the DC voltage to the device itself, and how is the maximum also? That's it.
Thank you. So thank you for the suggestion. Yeah, we will cover that. So for this the question cells after the specification. Example, in the unipolar side, we have 0 up to 34 volt, but for the bipolar side, we can go up 16 to minus 16 volt, and it can cover 500 milliamps plus on that. So covering the custom device, it needed you require uh, uh,
and capture at the same time, because the larger the channel, the larger the bandwidth, I believe. And then, once again, how about the support for the current IoT? Is it possible to access your device from, let's
Recording
say,
in
the
progress.
network? Okay, thank you very much.
Yeah, thank you for the question.
Yeah,
So
so
the
the
first
first
question is
question
in
is
parallel and how much the latency. So you have different devices also. If you see the X-Stack and X-SOM, the X1 AV, that one is very fast. Around I think the latest one 10 millisecond. But the 120 channel we have two devices, the X-Stack U and M. But now the range is around few milliseconds. We actually published a paper 2 years ago to drive several channels up to 1,000 channel parallel. Inside the box is actually each channel has its own measurement system. But in the exome wise, we actually parallelize what's called the chip. So each chip has its own controller, so it can be faster. But the fastest one probably the ATE one, because that's the one that we optimize for the high speed testing, and we can talk more later if you want to go deep. We can talk more later if you want to go deep to the technical specification. We welcome for that. The second one is about support IoT. Okay. Support IoT. So to control the device, most of the device is controlled through IP address that you can actually connect to your switch or internet. And then you can access it through the IP address. So yes, it's possible.
Okay, yeah, there's one more question.
Good afternoon. I'm Yashwant from Manipal Institute of Technology, India. So I have been in touch with your associates regarding the different hardware devices what you have, but still I have one question. So we are, I think, already evolved from 5G to 6G. So what is the challenge you got while designing and manufacturing of the equipment, 5G to?
Okay.
If it is a communication device, if you're planning for communication device.
Yeah, so probably the challenge now related to the bandwidth and also the packaging on the PIC is still very challenging even for the data centers, because one of the AI and data center infrastructure, the one that actually pull all the challenge. But I think some of the requirement there is to shrink the controller itself. If you see the box there, we have a client in Japan. It's actually, before they use our product, it was so big and it was very high power consumption. And they use our current box with lower power consumption for the next 5G deployment. And what they require next is actually to shrink that into the chip scale that we're currently working on it too. That's still a challenge. Thank you.
Okay, thank you for the question and also for the answer, of course. There's one more question from Pak Marlian.
Yeah, hello again, Pandri. I have
two simple questions. As I know, mostly your research team are Indonesians, right? So I just curious, wondering about how do you manage the Indonesian research team in order to make locally research design, right? And then global accepted equipment to catch a lot of countries. Next, with company tell every product. Yeah. Okay. Thank you.
Okay, thank you. Yeah, it's an interesting question, and thank you for that. A process in mouth. So the initial client was my friends, actually near our lab, who actually asked to build the device. And I asked him, okay, send me $2,500 today, and I will build for you. That's the first one. After I successfully delivered that product, his friend from other university institution is actually calling me to build more advanced device. And then I worked for that and delivered the product. And after that, actually, we got a lot of feedback from previous, users, and we developed with the contact around the world who we are. But we use initially we were in Sydney, Australia, right? So that's also giving us more credibility when they contacted us. But the one thing is very interesting part when we've been contacted by U.S. Army at that time. Uh, they connect us through our website, and they chat through our chat, and I was the one who answered it, and he asked about the specification and how you can deliver. And I just realized when he asked the quotation, he put the US.mil, and we realized we're still in the garage, but we need to ship to them. And they don't care about it. They care about what your solution fit to them. Like uh, uh, solving their problem. Basically, we provide a solution that nobody can provide for that. And this is related to your second question, probably the competitor, right? The competitor on the market mostly depends on not the latest technology and the density. We have some customers that we very interesting. Also, question that we asked to them is from MIT. The MIT postdoc at the time, we asked like, why you choose our product than other like Keysight, National Instrument, and so on, right? And the simple answer, because it's fit for our PIC. This device looks like developed for the PIC community that we are the users. So as you see before, the product itself is come from my own experiment. So I understand how difficult it is to control the PIC if you use many kitly, very expensive one. If you need 100 channel on single chip to test it, it's very frustrating. And they don't want to buy like 100 rack of that equipment, basically, to simplify not only the cost, but also the efficiency of the program itself. Yeah. Is that answer all the questions? Okay, thank you.
Okay, thank you very much. We have limited time, but I still have two questions from me. So my first question is still related to the question from Pak Marlin about your experience, because I know you have a lot of experience working in different countries like Korea, Australia, America, US. And can you give us like a short comments about difference between the research ambient between those countries, including in Indonesia, of course. And my second question is, you've shown us many excellent customers globally around the world, but I haven't seen any from Indonesia. Do you have any example from Indonesia? Thank you.
Okay, yeah, thank you. Yeah, so yeah, the first question about our journey related to how what's called we we develop and we is our strength with the outside the world. I think our experience, my experience working with different countries or different continent is very different. In South Korea, it was very tough, very hard. But at the time, that was my first job because I got the scholarship from the company. I need to work for them. Um, but what I see was like for learning journey for me. We worked. There was a long work time, but it was fun because it's new challenge for me. And if I compare with the in Australia, for example, it's more about build a thinking. So how you think very clearly about the problem, understand the problem, and how you create solution, but not really into a long hours. Comparing to the US is kind of combination of both. Okay, so I work at IBM Watson, and a lot of people like they work very hard but they enjoy it. I see a lot of people. I used to um, get lunch with all the members every day and see they graduate from MIT, Berkeley, Caltech, and everyone like talking about very deep tech. But they really enjoy. But I really enjoy different continent working environment. But in Indonesia now we try to bring that culture actually, not the culture of uh, long hours. Not only that, but we try to combine with the mindset of deliver in on time basically. So if you have something that customers need within the timeline, so we need to focus to deliver on that specific time. And that's always in our DNA since the beginning. We don't care at that time where we work for the first time, but as long as the customer is happy and the specification meets the requirement. And also related to Pak Marlin question, the first one, we recruit the best team members in our team. Most of them is actually international winners in robotics, in chip design, and that we join with us right now. So it's part of that culture. And the second one probably related to
That's some example for the case in Indonesia.
yeah, case Indonesia. Actually, we have delivered some of the equipment in Indonesia. We delivered to ITERA in Sumatra, but also we have manufactured one of the hardware in Bali also. We actually deliver thousands of devices already here, but not what we present here. So it's part of our business journey basically. So what we have.
Okay, thank you very much. That's very good experience and very good answer. Okay, I think because we have limited time, I think I have to finish our session here. Thank you again. Thank you very much, Pak Andri, for delivering talk. Let's give us applause for Pak Andri. And on behalf of the committee, I would like to give you some token of appreciation.
Okay, now I also would like to invite Professor Nasrullah Army to come forward to give the token of appreciation to next slide. Thank you, Dr. Andri Mahendra and Professor Dr. Natalaita for having delivered the last of the patron talk. And I also would like to say thank you to Next Lab for having supported our conference. And moving forward, now we are already finished all of our program, and now we are entering the closing ceremony for ICRAMET 2025. Then I would like to invite our technical program committee, Dr. Budiman Putra Rohman, and also Professor Yusuf Nurwijayanto, PhD, to present the awards from ICRAMET 2025.
Ini kan masih yang ngomong biar PPC chair masih akan ngomong dulu udah pulang. Udah Haris Maska udah yang apa? Best apa? Yang dari Irak. Ya.
Good afternoon, ladies and gentlemen. I'm Budiman Putra Rohman, the Deputy Chair of ICRAMET 2025. Now we come to one of the most exciting moments, the award announcement. So in this award announcement, we will award give the three awards: Best Paper Awards, Best Presenter Awards, and the Most Engaging Presenter Awards. And let's start with the Best Paper Awards. So the Best Paper Award recognizes outstanding research with exceptional innovation and contribution. And the winner of the Best Paper Award is... Okay, please give big applause for Mr. Muhammad Safa Jawad from Altaf University College, Iraq, and the team for the paper titled Comprehensive Analysis of Near Ultrasonic Acoustic Channel for Short Range High Data Rate Aerial Acoustic Communication. Congratulations for Mr. Muhammad Safa Jawad and the team. And the author presents? No? Okay. So we move to the next award, the Best Presenter Award. So the Best Presenter Award honors speaker who deliver their high quality work with clarity, confidence, and professionalism. And the Best Presenter Award is given to Miss Mariska Regina Christophera Hau from Bina Nusantara University Indonesia, ASU School of Engineering Indonesia, with a paper titled Smart Paint Localization, a hybrid approach using embedded vision and real-time laser guidance. Miss Mariska, present now? So, please.
Yes, I'm present.
Okay, Miss Mariska, congratulations for your awards.
Thank you very much.
Please give big applause for the Miss Mariska. Next. Okay. So the last awards, the Most Engaging Presenter Award. So this award honors the speaker who can present their research interactively to the audience. And the winner of the Most Engaging Presenter Awards is given to Mr. Yaswan Nanjapa from Manipal Institute of Technology, India, for paper entitled Orang Rings Underwater Energy Harvesting Power Bank System for Multi-Source Application. Please give a big applause for Mr. Yaswan. And I would like to invite Professor Yusuf Nur Wijayanto to give the certificate. Okay, thank you, Mr. Yaswat and Professor Yusuf Nur Wijayanto. I return back to the MC, Miss Dita. Thank you.
Dr. Budiman.
Kameranya nggak bisa digeser, kamera ini nanti lah. Itu soalnya nggak kelihatan banget ditanya. Oh ya udah.
Now, I would like to invite our chair, Dr. Widya Budiawan, to come forward to present the awards for the best participants.
Dia menanya, Mbak Putri mana sesuatu yang kita semua tidak tahu.
Thank you. Good afternoon, everyone. So now I will announce the best participants. So silently the committee just observe the participants who attend on site, and we decide will have so like active and consistent to stay and the forum, and then consist follow the talk. So the first best participants come to Dr. Iman Firmansyah. And then another best participant is Mr. Budi Nugroho. Please come to backstage. My come to. Go. Okay, thank you for you joining us and make this conference more. I don't know what is the more interactive. Yeah. Okay. Thank you very much. Okay. Makasih. Ya, makasih, Pak. Oh.
Congratulations for all of the winners. And also thank you for the winners, but also participants who made the ICRAMET 20 and 25 conference lively and really active. And we would like to express our gratitude against our patrons, to Andrik Su, Mitronik Jaya, PT Enforce, PT Nixlab Global Industri, PT WAP Andalan Indonesia, PT Serviam Abadi Murni, PT Radar Telekomunikasi Indonesia, PT Mitra Sistematika Global, PT Sabta Cakra Manunggal, PT Merck Chemicals and Life Sciences, PT Dimtek Lab Science Indonesia, and PT Bank Rakyat Indonesia. So I think that we will still have some patrons that already here with us. So I would like to call representatives from our patron, PT Bank Rakyat Indonesia, to come to the stage. Professor Yusuf Wijayanto, please come to the stage. Also that I believe that we also have representative from PT WAP Andalan Indonesia. Here with us, is it? Come to the stage. Okay, now Professor Nasrul Armi, please come forward. Ini semua timnya. Thank you. Also, I would like to invite the representative from PT Radar Telekomunikasi Indonesia, RTI, to come forward. Okay. Siap, Pak Yusuf lagi. Widya, ya. I think I would like to invite the chair. Is Mr. Widya is here? Mana plakat? Wait a bit. I would like also to invite all the representative of our patrons and all of their staff, if they're present for exhibition room. Yeah, we will have the group photo for our patrons. Yes. Yes. Yeah, for patrons, maybe from Andritsu from Rohde and Swartz, and you can call out your teams if you want, or representatives is up to you. Also PT Nixlab Global Industri, PT WAP Andalan Indonesia, PT Serviam Abadi Murni, PT Radar Telekomunikasi Indonesia, PT Mitra Sistematika Global, PT Sapta Cakra Manunggal, PT Merck Chemicals and Life Sciences, PT Dreamtech Lab Science Indonesia, and PT Bank Rakyat Indonesia. Ada lagi? Prof. Yusuf, National Army, and our chair, please come forward. So, photo. Baru. Thank you again for our patrons that for supporting our ICRAMET 2025, and also hope that we can continue our collaborations and our partnership in the future. Okay, now we have come to the end of the International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications. And now we will have the closing statements from the head of Research Center for Electronics, National Research and Innovation Agency, to give us the closing statement for ICRAMET 25.
It's time to close ya. Oke, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen, respected speaker, distinguished guests, lecturers, academics from various universities and institutions, as well as participants of the conference, both those present in Bandung or those attending virtually. Let us raise our gratitude to thanks to God Almighty for the successful completion of the 14th International Conference on Radar, Antenna, Microwave, Electronic, and Telecommunication, ICRAMET 2025, which has been held smoothly for the past 2 days. We have followed to the presentation from our keynote speakers, Associate Professor Satria Zulkarnain Bisri, Mr. Adi Bramantio, Professor Dr. Nasrul Armi, and Dr. Kim Hee Won. We have also heard presentation from various presenters across 7 tracks, and these papers will be published in IEEE Explore. We would like to express our gratitude to all the speakers and presenters, and we hope that the knowledge share will be followed up and contribute to the growth of research and electronic and telecommunication. Thank you also to the invited guests and participants who have joined us either in Bandung or online. Furthermore, our thanks go to our sponsor and patrons. The first one is IEEE Indonesia Sections, Rode and Swartz, Andritsu Unitronic, Jaya, Mars System Integrasi, PT Nix Lab Global Industry, PT WAP Andalan, Indonesia, PT Servian Abadi Murni, MSG Kisait, RTI Group, PT Sapta Cakra Manunggal, Dream Teach Lab Science Indonesia, BRI, and Merck. We hope that your participation serve as a valuable contribution, especially to research in electronic and telecommunication. Last but not least, I would like to express my sincere appreciation and thanks to the organizing committee for successfully carrying out this conference smoothly. Finally, we apologize where any shortcoming or things that were not to your satisfaction during the organizing and interaction of at this conference. With say Alhamdulillahirabbil alamin, I hereby declare the 14th International Conference on Radar, Antenna, Microwave, and Telecommunication. Radar, Antenna, Microwave, and Electronic and Telecommunication ICRAMET 2025 with this next generation with theme next generation electronic and telecommunication for advanced connectivity and sustainable solution officially closed. I hope we can meet again. I hope we can meet again in the 15th International Conference at Radar, Antenna, Microwave, Electronic, and Telecommunication in the next year. Thank you and Assalamualaikum warahmatullahi wabarakatuh.
Okay, now that we've reached the end of ICRAMET 25, and I also, as the host, would like to thank all of you again for your participations and enthusiasm for this conference. I hope the talks and discussions we had in these 2 days will be beneficial for you in your future works. And finally, we will have photo groups again outside. So please, we can go outside in the photo booth. And afterwards, we still have some snacks outside. So if you still want to have some snack, then you can have the refreshment outside. Okay, so let's move and take the photo group.